Imagine for a moment that every time you look up at the stars, you're seeing only half the picture, that what we think we understand about the universe is built on foundations we can't fully see or explain. It's a humbling thought, isn't it? For centuries, we've mapped galaxies, traced the echoes of the Big Bang, and built elegant theories to describe the cosmos. Yet today, some of the most brilliant minds in science are quietly questioning whether we've been missing something profound all along. These aren't small gaps in knowledge, they're cosmic blind spots, vast and mysterious, hiding in the very fabric of reality. And what's truly thrilling is this: the answers we're chasing could rewrite not just astronomy, but physics itself. Welcome to a journey into the deepest mysteries of cosmology. We're going to explore the questions that keep astrophysicists up at night, the strange, almost invisible forces like dark matter and dark energy that make up most of the universe, yet slip through our finest instruments. We'll confront puzzling contradictions, like why the universe is expanding faster than our models predict, and why there's something rather than nothing at all. These aren't just academic curiosities. They speak to the fundamental nature of existence, of space and time, matter and energy. And in exploring them, we aren't just learning about the cosmos, we're rediscovering how much wonder is still left to uncover. So whether you're someone who's always been captivated by the night sky, or you're simply curious about the biggest questions we can ask, you're in the right place. By the end of this video, you won't just have a list of facts, you'll see the universe differently. You'll understand why these blind spots matter, why they captivate scientists and dreamers alike, and how solving them could change everything we know. So let's begin this exploration together, with open minds and eyes lifted upward, ready to uncover what's been hiding in plain sight all along. Picture a galaxy spinning in the depths of space. Based on the amount of visible matter, the stars, the gas, the dust, the laws of physics tell us that this galaxy should be flying apart. The gravity generated by everything we can see simply isn't strong enough to hold it all together. And yet it spins on, perfectly stable. The only explanation is that there is something else there, something we cannot see, providing the extra gravitational glue. This invisible something is dark matter. It doesn't absorb, reflect, or emit light, making it completely undetectable to our telescopes. Yet its gravitational influence is undeniable, not just in individual galaxies, but in the way entire clusters of galaxies move, and in how light bends around them in a phenomenon known as gravitational lensing. We can map its distribution across the cosmos by watching how it warps the fabric of space-time itself, creating a shadowy skeleton upon which the visible universe is built. The hunt to identify what dark matter actually is has become one of the most compelling scientific quests of our time. The leading hypothesis is that it consists of a new, yet-to-be-discovered type of elementary particle, one that interacts with ordinary matter almost exclusively through gravity. Scientists have given these hypothetical particles names like WIMP, or weakly interacting massive particles. To find them, researchers have built extraordinarily sensitive detectors and placed them deep underground in abandoned mines and beneath mountains, shielding them from the constant cosmic ray shower that bombards the Earth's surface. These experiments wait for the incredibly rare occasion when a dark matter particle might bump into the nucleus of an atom in the detector, sending a tiny signal. Other approaches look to space, with telescopes on satellites scanning the skies for the unique gamma-ray light that could be produced if dark matter particles annihilate each other when they collide. And then there are efforts to create dark matter in powerful particle accelerators like the Large Hadron Collider, hoping to conjure it into existence for just a fraction of a second. Yet, despite decades of searching with increasingly sophisticated technology, dark matter remains elusive. Not a single experiment has returned a confirmed, definitive detection. This persistent failure has led some physicists to consider even more exotic possibilities. Could dark matter be something stranger than a particle? Perhaps it's related to primordial black holes formed in the first moments after the Big Bang. Or maybe our understanding of gravity itself is incomplete, and what we perceive as dark matter is actually a sign that Einstein's theory of general relativity needs to be modified on the largest scales. These alternatives are fascinating, but they too come with their own set of challenges and lack concrete evidence. This ongoing mystery forces a profound humility. We have to accept that the majority of the matter in the universe is made of something entirely foreign to our experience, a substance that defines the cosmic landscape yet refuses to reveal its identity. Solving this puzzle wouldn't just be about filling in a blank in our textbooks. It would represent a fundamental revolution in physics. Discovering the nature of dark matter could open a door to a whole new realm of particles and forces, a hidden sector of reality that has been there all along, shaping the universe in ways we are only beginning to perceive. It would be a triumph of human curiosity and ingenuity, a testament to our desire to understand the hidden workings of the cosmos. And as we grapple with the nature of this invisible matter that holds galaxies together, it naturally leads our curiosity to an even more dominant and mysterious force shaping the universe's destiny. If dark matter is the invisible scaffolding holding the cosmos together, then dark energy is the mysterious force relentlessly pushing it apart. This discovery at the end of the 20th century was so shocking it upended our entire cosmic narrative. For decades, the prevailing assumption was that the universe's expansion, set in motion by the Big Bang, must be gradually slowing down over time. The collective gravitational pull of all the matter in the cosmos was thought to be acting like a cosmic brake, gently tugging on everything. The big question was simply whether there was enough matter to eventually halt the expansion entirely, leading to a potential big crunch, or if it would just slow to a crawl. But then, two independent teams of astronomers observing distant supernova made a Nobel Prize-winning discovery. They found that the expansion of the universe isn't slowing down at all. It's accelerating. It's as if you tossed a ball into the air, and instead of falling back down, it shot away from you faster and faster into the sky. This observation pointed to the existence of a repulsive force, a kind of anti-gravity, permeating the very vacuum of space. We call this force dark energy, and it makes up a staggering 68% of the entire universe. So what could it be? The leading and simplest explanation is the cosmological constant, an idea Einstein himself introduced and later called his biggest blunder. He had initially added it to his equations of general relativity to force a static, unchanging universe, which was the belief at the time. When the universe was found to be expanding, he discarded the idea. But now it's back in vogue. In this view, dark energy is the energy intrinsic to empty space itself. According to quantum physics, a vacuum isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. This quantum activity could be generating a constant energy density that pushes space apart. The enormous problem, however, is that when physicists try to calculate how strong this vacuum energy should be based on theory, the number they get is wrong by a factor of 1 followed by 120 zeros. It is arguably the worst prediction in the history of science. This cosmological constant problem suggests a profound gap in our understanding. Other theories propose that dark energy isn't constant at all. It could be a dynamic field nicknamed quintessence that changes over time. This would mean the strength of this repulsive force could vary, potentially increasing or decreasing as the universe ages. Figuring out which model is correct is one of the most urgent goals in cosmology because the nature of dark energy dictates the ultimate fate of everything. If it is a true cosmological constant, the universe will continue expanding at an ever-increasing rate, leading to a cold, dark, and lonely heat death, where galaxies are pulled so far apart that the sky will eventually go black for any future observers. If it's something more volatile, the outcome could be even more dramatic, a big rip where the fabric of spacetime itself is torn apart, shredding galaxies, stars, planets, and even atoms in a final, violent end. This isn't just abstract theorizing. It's a quest to understand the destiny of all existence, a question that forces us to confront the very fundamentals of gravity, space, and time. But just as we're grappling with the nature of these two great cosmic unknowns, a more immediate and unsettling problem has emerged, one that strikes at the very heart of our ability to measure the cosmos. For nearly a century, astronomers have relied on a single, crucial number to understand the history and future of the universe, the Hubble constant. This number represents the rate at which the universe is expanding today. It's the speedometer reading for the cosmos, and for decades, we've been refining our methods to measure it with ever greater precision. The shocking development is that our two most trusted methods for measuring this fundamental value are now giving us two different answers. And the more we improve our measurements, the wider the gap between them becomes. This isn't a small, marginal error. It's a growing discrepancy that has now reached a level of statistical significance that can't be easily ignored. It's a crisis that cosmologists have poetically named the Hubble Tension. On one side of this divide, we have a method that looks back to the very infancy of the universe. By studying the cosmic microwave background, the faint afterglow of the Big Bang, with exquisite instruments like the Planck satellite, we can see the universe as it was just 380,000 years old. The subtle patterns imprinted in this ancient light are a cosmic blueprint, allowing us to extrapolate forward through 13.8 billion years of cosmic evolution to predict what the expansion rate should be today. This method is incredibly powerful and has given us our most precise standard model of cosmology. It provides a very specific and very confident value for the Hubble constant. On the other side, we have a method that measures the universe's expansion directly in our own cosmic neighborhood. Astronomers use what are known as standard candles, objects like Cepheid variable stars and Type Ia supernova, whose intrinsic brightness we believe we understand. By measuring how bright these objects appear from Earth, we can calculate their distance. By then measuring how fast they are moving away from us due to the expansion of space, their redshift, we get a direct local measurement of the expansion rate. This technique is like measuring the current speed of a car with a radar gun, rather than calculating it based on its acceleration from a standing start. And this local measurement consistently gives us a faster expansion rate than the one predicted from the early universe. The most baffling part is that both methods are executed with incredible care and precision. Teams on both sides have checked and rechecked their work, accounting for every conceivable source of error. They've used new telescopes like the Hubble Space Telescope and now the James Webb Space Telescope to refine the local measurements. They've pored over the Planck data again and again, and the gap remains. It's as if two of the world's most accurate clocks, built by master watchmakers, are ticking at undeniably different speeds. This tension suggests that our extrapolation from the early universe to today might be missing a piece of the puzzle. Perhaps there is something in our cosmological model that isn't quite right. Maybe dark energy isn't constant but is evolving in an unexpected way, adding a new kick to the expansion. or perhaps dark matter has properties we haven't accounted for. Some have even proposed more radical ideas, like the existence of a new type of neutrino or another unknown particle that was present in the early universe and altered its evolution. This isn't just an academic disagreement, it's a potential crack in the foundation of modern cosmology, a signpost pointing toward physics we have yet to discover. It forces us to confront a humbling possibility that our most trusted tools, while incredibly powerful, might be measuring a reality that is more complex and mysterious than our current models can describe. This profound mystery of why we exist at all is known to physicists as baryon asymmetry. The laws of physics, as we currently understand them, treat matter and antimatter as nearly perfect mirror images. For every particle of matter created in the high-energy forge of the Big Bang, an antiparticle should have been created alongside it. Think of it like a cosmic coin toss happening an unimaginable number of times, each time landing perfectly on its edge. The expected outcome was a perfect symmetry, a universe where every particle found its antimatter twin, leading to mutual annihilation in a flash of pure energy. The end result should have been a vast, empty cosmos filled with nothing but radiation, a silent, sterile expanse with no stars, no planets, and certainly no one to ponder its emptiness. And yet, here we are. So what happened to break this perfect symmetry? How did the universe tip the scales ever so slightly in favor of matter? The answer seems to lie in a fundamental requirement laid out by the physicist Andrei Sakharov. For matter to win out, three conditions had to be met in the early universe. First, there had to be a process that treated matter and antimatter differently, violating what's known as charge parity or CP symmetry. Second, this process had to occur during a period when the universe was out of thermal equilibrium, meaning it wasn't in a stable, uniform state. And third, it had to involve interactions that change baryon number, which is essentially a conserved quantity for matter. It's a tall order, and finding a process in nature that satisfies all three has been the holy grail of particle physics for decades. We do have one known but tiny piece of the puzzle. In certain rare subatomic processes involving particles called kaons and B-mesons, we have observed CP violation. This means that these particles and their antiparticles decay at slightly different rates. It's a clear demonstration that the universe does, on occasion, distinguish between matter and antimatter. The problem is that the amount of CP violation we've measured in our laboratories is infinitesimally small, nowhere near enough to account for the overwhelming dominance of matter we see in the cosmos today. It's like finding a single drop of water and trying to explain the existence of all the oceans. So while we've found a mechanism, it's tragically insufficient, pointing toward the existence of a much larger, more dramatic source of symmetry breaking that must have occurred in the extreme conditions just after the Big Bang. This has led theorists to propose some of the most fascinating ideas in modern science. One leading candidate is a process called leptogenesis. This theory suggests that the initial asymmetry didn't start with matter at all, but with neutrinos, specifically heavy, right-handed neutrinos that we have not yet discovered. These hypothetical particles could have decayed in the early universe in a way that created a slight excess of leptons over anti-leptons. Through a complex cascade of interactions, this lepton asymmetry could then have been converted into the baryon asymmetry we see today, essentially using the weak nuclear force to transform a small imbalance in one type of particle into the vast dominance of the matter that makes up our world. Other theories look to grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces, predicting the existence of new particles called X-bosons that could also decay asymmetrically. The staggering implication of this puzzle is that our entire existence hinges on a 1 in a billion imbalance. For every billion annihilations that occurred in the first second of the universe, a single particle of matter survived. That is the fragile margin from which every galaxy, star, planet, and person ultimately emerged. It is the ultimate fine-tuning problem, a fundamental skew in the laws of nature without which reality would be a void. Unraveling this mystery wouldn't just complete a chapter in a textbook, it would reveal entirely new laws of physics, potentially exposing new particles or forces that played a role in those first critical moments. It is a quest to answer the most profound question of all: why is there something rather than nothing? This search for our own cosmic origin story pushes us to look even further back, to the very instant of creation itself. To explain the universe we see today, its vast scale, its startling uniformity, its flat geometry, we are forced to confront an idea so radical it seems like something from science fiction. This is the theory of cosmic inflation, which proposes that in the very first sliver of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. Imagine a tiny subatomic speck, smaller than a single proton, suddenly inflating to the size of a marble in an almost incomprehensibly short time. This isn't expansion into space. This is the rapid stretching of space itself, a monumental growth spurt that set the stage for everything that followed. Inflation elegantly solves several of cosmology's biggest puzzles at once. It explains why the universe is so uniform. Regions now on opposite sides of the sky were once close enough to reach a common temperature before being violently wrenched apart. It accounts for why the geometry of the universe appears so perfectly flat, and it provides the mechanism for the origin of all structure. The quantum fluctuations that were present in that tiny seed were stretched to cosmic proportions, eventually becoming the gravitational seeds for galaxies and galaxy clusters. It's a powerful, almost magical solution, but it comes with a profound catch. We have no idea what actually caused it or, just as importantly, what made it stop. The leading theoretical explanation for this dramatic event involves a hypothetical entity known as the inflaton field. Think of this as a unique energy field that temporarily dominated the entire cosmos. In this model, the universe began in a state of false vacuum, a high-energy condition that is unstable, like a ball perched precariously at the very top of a hill. This state possessed a peculiar property. Its energy density caused a repulsive gravitational effect, driving the exponential expansion of space. As inflation proceeded, the inflaton field slowly began to decay, rolling down its energy hill. When it finally reached the true vacuum state at the bottom, this enormous potential energy had to go somewhere. According to the theory, it was dumped into the universe, reheating it and filling it with the hot plasma of particles and radiation that would become the raw material for the Big Bang's subsequent evolution. In this view, the Big Bang wasn't the very beginning, but the spectacular finale of the inflationary epoch. Despite its incredible explanatory power, the inflaton field remains entirely speculative. No experiment has detected it, and we have no direct evidence that it exists. This has led some cosmologists to explore compelling alternatives. One fascinating idea is the concept of a bouncing cosmology, which suggests our universe might not have begun from a singularity, but could be cyclic. In this scenario, a previous universe contracted in a big crunch, but instead of collapsing to a point of infinite density, it reached a maximum density and then bounced back outward, initiating our own expansion. Other theories propose that our universe is just one bubble in a vast, eternally inflating multiverse, where new bubble universes are constantly budding off from an ever-expanding background spacetime, each with its own random physical laws. These ideas push the boundaries of testable science, venturing into the realm of profound metaphysics. The blind spot of inflation's origin forces us to confront the ultimate question: what, if anything, came before the Big Bang? It challenges the limits of our physics and our imagination, reminding us that our most successful stories about creation are still just that, stories, waiting to be confirmed or overthrown by the next great discovery. But this seemingly elegant solution for dark energy immediately slams into what many physicists consider the most embarrassing and profound problem in all of theoretical physics: the cosmological constant problem. To understand the sheer scale of this puzzle, we need to consider what our two most successful theories tell us about the energy of empty space. On one hand, we have quantum field theory, which describes the behavior of particles and forces at the smallest scales. This theory tells us that the vacuum of space is not truly empty. It is a seething, bubbling foam of virtual particles. These are particle-antiparticle pairs that constantly pop into and out of existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and returning it. This quantum jitter is not just theoretical. We can observe its effects in experiments like the Casimir effect, where two metal plates placed very close together in a vacuum are gently pushed together by the pressure of these virtual particles fluctuating outside them. When physicists attempt to calculate the total energy density that this endless quantum activity should contribute to empty space, the number they arrive at is staggeringly, monumentally huge. On the other hand, we have cosmology and general relativity, which describe the universe on the largest scales. Through observations of the universe's accelerating expansion, we can measure the actual effective energy density of the vacuum. This is the value we plug into Einstein's equations to make dark energy work, and this observed value is incredibly, inexplicably small. Now, the problem is this: the value predicted by quantum physics is larger than the value observed by cosmology by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This isn't just a small rounding error. It is the largest discrepancy between theory and observation in the entire history of science. To put it in perspective, if the predicted value were the size of the entire observable universe, the observed value would be smaller than a single atom. It is a failure of prediction so catastrophic that it screams one undeniable truth: we are missing something fundamental. Either our understanding of the quantum vacuum is deeply flawed, or our understanding of gravity is incomplete, or both. The search for a solution has led to some of the most creative and desperate ideas in physics. One possibility is that there exists a mysterious cancellation mechanism, some unknown symmetry or principle that makes all these enormous quantum contributions to vacuum energy cancel each other out with unimaginable precision, leaving behind only the tiny trickle we observe. Another, more radical idea is that we need to completely abandon the concept of a cosmological constant and look for an entirely new framework that somehow makes the vacuum energy immune to these quantum fluctuations. This blind spot is more than just a mathematical annoyance. It represents a yawning chasm between the world of the very small and the world of the very large. Our theory of particles and our theory of gravity are fundamentally at odds, and until we can bridge this gap, a complete picture of the universe will remain out of reach. This profound disconnect between our most successful theories forces us to look at other areas where prediction and observation clash, such as in the very formation of the structures we see around us. When we run supercomputer simulations of how the universe evolves, based on our best understanding of dark matter and gravity, they produce a very specific prediction for what a galaxy like our own Milky Way should look like. These simulations show that large galaxies should be surrounded by a vast swarm of smaller satellite galaxies, hundreds of them, all held in orbit by the immense gravitational pull of the primary galaxy's dark matter halo. It's a beautiful, hierarchical picture of cosmic structure, but when we point our telescopes at the actual Milky Way and our neighboring galaxy, Andromeda, the reality is starkly different. We don't see hundreds of satellite galaxies, we see dozens. This glaring mismatch between what our theories predict and what our telescopes reveal is one of cosmology's most persistent puzzles, aptly named the missing satellites problem. For a long time, a simple explanation seemed plausible. Maybe the missing satellites are there, but they're just too faint for us to see. Perhaps they are composed almost entirely of dark matter, with very few stars to light them up. This idea drove a dedicated search for these so-called dark galaxies. And while our surveys have indeed discovered many new, incredibly faint, ultra-faint dwarf galaxies, the numbers still don't add up. Even accounting for these dim objects, the total count of observed satellites falls far short of the simulated multitudes. The problem isn't that we can't see them, it's that they simply don't seem to exist in the numbers our models demand. This forces us to confront a more exciting possibility. The error isn't in our observations, but in our fundamental assumptions about how the universe works. This discrepancy points a finger directly at the nature of dark matter itself. The standard cosmological model is built on the idea of cold dark matter. Cold means the hypothetical particles move relatively slowly, which allows them to clump together easily, forming those numerous small-scale gravitational wells that should eventually host small satellite galaxies. But if dark matter were instead warm, consisting of lighter, faster-moving particles, it would change everything. Warm dark matter would have more energy, preventing it from clumping on the smallest scales. It would smooth out the inner regions of dark matter halos, effectively wiping out the smallest clumps and resulting in far fewer satellite galaxies, a prediction that aligns much more closely with what we actually see. While warm dark matter is an attractive solution, it's not without its own challenges, as it can struggle to explain other observed features of galactic structure, leaving cosmologists to carefully weigh the evidence. Alternatively, the issue might not be with dark matter's temperature, but with its social life. The standard model assumes dark matter is essentially non-interacting. Particles of dark matter pass right through each other and normal matter without a whisper. But what if that's not true? What if dark matter particles can interact with each other through some unknown force, a kind of dark light or dark electromagnetism? These self-interactions would act as a smoothing mechanism, scattering particles and erasing the very smallest clumps within a galaxy's halo. This would also naturally solve another related puzzle: the fact that the dense centers of dark matter halos in dwarf galaxies appear less cuspy and more smoothed out than simulations predict. The idea of a rich, complex dark sector with its own forces and particles is speculative but thrilling, suggesting an entire shadow universe of physics operating alongside our own. Of course, the solution might not require changing dark matter at all. Perhaps the problem lies in our understanding of the messy astrophysics of galaxy formation itself. The simulations predict dark matter clumps, but turning a dark matter clump into a visible galaxy requires gas to fall in, cool down, and form stars. It's possible that the smallest dark matter halos are there, but they failed to ever form stars. How? The intense ultraviolet radiation from the first massive stars and galaxies in the early universe could have heated the gas throughout the cosmos, making it too hot to settle into the smallest gravitational wells. Or supernova explosions in a dwarf galaxy's first burst of star formation could have blown out all of its remaining gas, shutting down further star formation and rendering it virtually invisible. In this view, the satellites aren't missing, They're just dark, failed galaxies that never manage to light up. Solving this puzzle is more than an academic exercise. It's key to understanding the full life cycle of cosmic structures. By studying the population of satellite galaxies, both the ones we see and the ones we don't, we are conducting a crucial test of the entire cold dark matter paradigm. Each newly discovered ultra-faint dwarf, each precise measurement of its dark matter content, and each increasingly sophisticated simulation brings us closer to an answer. The missing satellites problem brilliantly illustrates that galaxies are not just collections of stars, but the delicate products of a long and complex dance between dark matter's relentless gravity and the often violent astrophysics of luminous matter. This intricate interplay between the seen and the unseen defines the cosmic landscape, and nowhere is the presence of nothingness more defining than in the vast empty regions known as cosmic voids. While we often focus on the glittering structures of the cosmos, the galaxies, the clusters, the brilliant supernova, some of the most profound mysteries are actually found in the vast, empty spaces in between. Imagine the universe not as a uniformly scattered collection of stars, but as a colossal cosmic web. This web is made of dense filaments of dark matter and galaxies, intersecting at massive clusters, but it also contains enormous hollow bubbles. These are the cosmic voids, regions of space that are staggeringly, almost unimaginably empty. They are the great deserts of the universe, some stretching hundreds of millions of light years across. To put that in perspective, if our Milky Way were a single grain of sand, one of these voids would be the size of a vast, empty cathedral. And within these voids, the density of matter can be less than a tenth of the cosmic average. They are not just empty, they are the emptiest places that exist. But how does nothingness become such a powerful player in shaping the cosmos? The existence of these voids is a direct consequence of the initial conditions set by the Big Bang and the relentless pull of gravity. In the early universe, tiny quantum fluctuations were stretched to cosmic scales by inflation, creating slightly denser and slightly less dense regions. Over billions of years, gravity acted as a cosmic amplifier. Matter was pulled irresistibly toward the denser regions, which grew into the filaments and clusters of the cosmic web. In doing so, it drained matter away from the less dense regions, evacuating them and leaving behind these immense growing voids. They are the negative image of the universe's structure, defined not by what is there, but by what has been siphoned away. Their very emptiness is a testament to the power of gravity to sculpt the universe on the grandest of scales. Far from being passive, empty bubbles, these voids actively influence the evolution of the galaxies within and around them. A galaxy that forms inside a void, often isolated and alone, is called a void galaxy. Without the constant gravitational interactions and collisions that are common in dense clusters, these galaxies evolve in a much more sedate, peaceful environment. They tend to be slower to convert their gas into stars, often appearing younger, bluer, and more pristine than their cousins in the crowded galactic cities. Studying these isolated void galaxies is like finding a quiet village untouched by the bustle of a metropolis. They offer astronomers a unique laboratory to understand galaxy evolution in its simplest, most undisturbed form, free from the complicated effects of a dense neighborhood. Perhaps the most mind-bending property of these voids is their effect on the expansion of the universe itself. We know that dark energy is causing the overall expansion of the cosmos to accelerate. But within a void, the local story is different. With so little matter inside them, the gravitational pull trying to slow down the expansion is incredibly weak. This means that within a void, space itself is expanding faster than the cosmic average. Conversely, in the dense clusters and filaments where matter is tightly packed, gravity is stronger, putting up more resistance and slowing the expansion relative to the voids. This creates a situation where the expansion rate of the universe isn't perfectly uniform. It has slight variations depending on whether you're measuring it from the depths of a void or the heart of a cluster. This phenomenon directly challenges our models and complicates our measurements of dark energy. If we don't properly account for these local variations in the Hubble flow, our global calculations for the expansion rate and the strength of dark energy could be subtly biased. This is why understanding nothingness is so critical. Cosmic voids are not just passive holes in the cheese of the universe, they are dynamic actors. Their growth, driven by the relentless push of dark energy against the pull of gravity, may actually hold the key to distinguishing between different models of dark energy. If dark energy's strength changes over time, if its dynamic quintessence rather than a constant, its effects would be imprinted on the rate at which voids grow and evolve. By meticulously mapping the sizes, shapes, and distribution of these voids across cosmic time, astronomers are using emptiness itself as a precision tool to probe the most mysterious force in the cosmos. The study of voids forces us to confront a beautiful paradox. To truly understand the universe's ultimate fate, we must look not only at its brightest structures but also into its deepest, darkest, and most empty reaches. And just as we use these vast, empty spaces to probe the cosmos, other mysterious signals are using them as a transmission medium, carrying encoded messages from across the universe. Amidst the vast cosmic voids and the grand architecture of the universe, there exist events so brief and powerful they challenge our very understanding of physics. These are fast radio bursts, or FRB. Imagine if all the energy our sun releases over several decades were compressed into a single, blinding millisecond flash of radio waves. That is the staggering power of an FRB. They arrive from galaxies billions of light years away, a fleeting signal that travels across the cosmos for eons, only to scream past our telescopes in less time than it takes to blink. The first was discovered in 2007, hidden in archival data from the Parkes Radio Telescope in Australia, and for years many astronomers wondered if it was a glitch, a one-off anomaly. But then more were found, confirming we were witnessing a genuine and utterly mysterious cosmic phenomenon. What makes these events so captivating to scientists is their dual nature. Some FRBs are lone wolves, powerful, one-off bursts that erupt and are never heard from again. Others are relentless repeaters, firing off signals again and again, but with no predictable pattern. It's as if some cosmic switch is being flicked on and off at random by an unseen hand. This dichotomy is a major clue. It strongly suggests that there isn't just one single cause for all FRBs, but rather multiple types of sources or mechanisms capable of generating these incredible flashes. The repeater bursts, in particular, rule out any model that involves the catastrophic destruction of the source, like a single, final explosion. Whatever is making them is tough enough to survive its own incredible outburst and do it again. The hunt for the source of these bursts has become a modern-day cosmic detective story, with a list of suspects that reads like a roster of astrophysics' most extreme objects. The prime suspect for many of the repeating bursts is a specific type of neutron star called a magnetar. Neutron stars are the incredibly dense, collapsed cores of dead stars, and magnetars are a special class of them with magnetic fields so intense they are the strongest known in the universe. It's thought that these fields can become wound up like colossal springs until they suddenly snap, releasing a titanic starquake on the surface that could generate a shriek of radio waves powerful enough to be heard across the universe. This theory gained significant support when a magnetar within our own galaxy was observed producing an FRB-like burst, proving that at least some of these events can originate from these exotic objects. But magnetars can't explain everything. The sheer energy of some extragalactic FRBs, especially the one-off events, pushes the limits of what even a magnetar might be capable of. This has led astronomers to consider even more dramatic scenarios. Could some FRBs be the death cries of stars being shredded by supermassive black holes? Or the result of two incredibly dense objects, like neutron stars, colliding and merging in a catastrophic event that sends a final, powerful signal echoing into the void? The most exotic theories even venture into the realm of speculative physics, pondering whether these bursts could be signatures of cosmic strings, topological defects in the fabric of spacetime, or even, though it's a long shot, evidence of advanced extraterrestrial technology. While that last idea is highly speculative and considered unlikely by most scientists, the very fact that it can be seriously discussed highlights just how enigmatic these signals truly are. Beyond the mystery of their origins, FRBs have an incredibly practical and revolutionary use. They are nature's perfect tools for mapping the otherwise invisible universe. As an FRB signal travels across millions of light-years of intergalactic space, it passes through clouds of hot, diffuse gas and the faint magnetic fields that exist between galaxies. This material leaves a distinct fingerprint on the radio wave, causing it to scatter and disperse in a measurable way. By carefully analyzing the signal of a single FRB, astronomers can essentially perform a cosmic census. They can calculate the total amount of ionized material the burst passed through, providing a new way to weigh the elusive, missing baryons we believe are hiding in these vast intergalactic regions. Furthermore, if we can detect enough FRBs from different directions and distances, we can use them to build a three-dimensional map of the distribution of matter in the cosmos, charting the cosmic web itself in a way we never could before. This transformative potential is what turns a cosmic curiosity into a fundamental blind spot. Fast radio bursts are more than just a puzzle to be solved. They are a stark reminder of how much violent, energetic activity is happening in the universe that we don't yet understand. They represent a new kind of astronomy, one that deals in milliseconds rather than long exposures, forcing us to build telescopes and develop software that can catch these ephemeral cosmic whispers. Each new detection adds a piece to the puzzle, but the full picture remains elusive, a testament to the fact that the universe is still full of brilliant, explosive surprises. And as we grapple with signals that cross the cosmos in an instant, we are forced to confront a puzzle about the universe's very first light, and why it appears the same in every direction we look. Now, let's consider one of the most fundamental and elegant puzzles in all of cosmology, a problem that strikes at the very heart of our understanding of cause and effect. It's called the horizon problem, and to grasp it, we need to look at the oldest light in the universe, the cosmic microwave background. This faint afterglow, a snapshot of the universe when it was just 380,000 years old, is stunningly uniform. No matter which direction we point our telescopes, the temperature of this radiation is the same to within 1 part in 100,000. It's a sea of sameness, a thermal equilibrium that blankets the entire sky. And this is the problem. According to the standard Big Bang model without inflation, these regions of the sky on opposite horizons should never have been able to communicate with each other. Think of it like this: since the birth of the universe, light has had a finite amount of time to travel 13.8 billion years, but the universe has also been expanding during that time. When we trace the paths of two photons arriving from opposite sides of the sky, we find that their points of origin were separated by a distance far greater than light could have possibly crossed in the age of the universe. They are outside each other's cosmic horizon. They are like two people standing in distant cities, too far apart to have ever met or exchanged a letter, yet somehow wearing identical outfits, down to the very same scuff on their left shoe. How could regions that were never in causal contact have managed to coordinate their properties so perfectly? How did they reach the same equilibrium temperature if energy and heat never had time to flow between them? This apparent violation of causality was a monumental problem for the standard Big Bang model. It suggested that the universe, for some unknown reason, simply started in a state of perfect uniformity, a highly specific and seemingly fine-tuned initial condition that required an explanation. The most celebrated solution, proposed by Alan Guth and others in the early 1980s, is cosmic inflation. This theory posits that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. This isn't matter moving faster than light through space, which is impossible, but the fabric of spacetime itself stretching at a rate that outpaced the speed of light. This incredible growth spurt would have taken a tiny, microscopic patch of the early universe that was already in thermal equilibrium, a patch small enough for light to cross and smooth out any temperature differences, and inflated it to a size larger than our entire observable universe today. What we see as opposite horizons were once intimately connected, nestled together in that tiny, unified region before inflation violently stretched them apart. It's a beautifully elegant solution that explains the uniformity we see as a natural consequence of a rapid expansion. However, while inflation is the leading theory and has become a cornerstone of modern cosmology, it is important to remember that it remains just that, a theory. We have strong circumstantial evidence that supports it, like the specific patterns of tiny fluctuations it predicts in the cosmic microwave background, but we lack direct smoking gun proof. This has led some physicists to propose alternative and truly mind-bending solutions to the horizon problem. One of the most radical is the idea that the speed of light itself was not always constant. In these variable speed of light, or VSL theories, light traveled much faster in the very early universe. If the speed of light was effectively infinite for a brief moment, then there was no horizon. Every point could communicate with every other point instantly, allowing the entire cosmos to smooth itself out into a uniform temperature. After this period, the speed of light would have dropped to the constant value we measure today. This idea is far more speculative than inflation and comes with its own set of theoretical challenges, but it highlights the incredible creativity cosmologists must employ when faced with such a deep paradox. The horizon problem, therefore, is more than just a technical issue with a model. It is a profound blind spot that forces us to question our most basic assumptions about the early universe. It asks us to reconsider the nature of causality and whether the rules we take for granted today always applied. Did the universe begin in a state of perfect, inexplicable order, or was that order created by a dramatic physical process like inflation? Or do we need to rewrite the laws of physics to allow for fundamental constants to change? The answer doesn't just explain why the sky looks the same in all directions. It tells us something fundamental about the very first moments of time, pushing our inquiries into a realm where our current theories of gravity and quantum mechanics completely break down. This fundamental conflict between our two greatest theories of reality is perhaps the most significant unsolved problem in all of physics. On one hand, we have general relativity, Einstein's magnificent description of gravity as the curvature of spacetime itself. It paints the cosmos on a grand canvas, explaining the orbits of planets, the bending of light around galaxies, and the very expansion of the universe with breathtaking accuracy. On the other hand, we have quantum mechanics, the bizarre and counterintuitive rules that govern the subatomic world. It deals in probabilities, wave functions, and particles that can be in two places at once, and it has been verified with unimaginable precision in countless experiments. Both are spectacularly successful in their own domains. The problem is they are utterly incompatible. They speak different mathematical languages and make contradictory claims about the nature of reality. This means that in places where both theories must simultaneously apply, where immense gravity meets the infinitesimally small, our physics simply breaks down. These are the most extreme environments we can imagine, the crushing singularity at the heart of a black hole, and the fiery, dense first moment of the Big Bang. To understand what truly happens in these realms, we need a theory of quantum gravity, a single framework that can weave these two disparate descriptions into one seamless tapestry. The quest for this unified theory has led physicists down some of the most intellectually daring and mathematically complex paths in human history. The most famous contender is string theory. This approach proposes a radical idea that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating strings or membranes. The different vibrations of these strings, much like the different vibrations of a guitar string producing different notes, would manifest as all the different particles and forces we see: electrons, quarks, photons, and even the graviton, the hypothetical particle that would carry the gravitational force. In this elegant vision, gravity isn't a special case. It emerges naturally from the vibrations of these strings. However, the theory comes with staggering implications, most notably the requirement that the universe has many more dimensions than the three of space and one of time we experience. These extra dimensions, string theory suggests, are curled up or compactified into a space so small we cannot perceive them. While mathematically beautiful, string theory has been criticized for a lack of testable predictions with our current technology, leaving it in a realm of compelling speculation. Another profound approach is loop quantum gravity. If string theory tries to unify all forces by changing what matter is made of, loop quantum gravity takes a more direct path by quantizing the very fabric of spacetime itself. In this theory, space is not a smooth, continuous backdrop as Einstein described. Instead, it is woven from a network of tiny, discrete, one-dimensional loops. Think of it as a cosmic mesh or a spiderweb, where the intersections of these loops represent the smallest possible units of volume, a sort of atom of space. Time, too, is granular, advancing in tiny, indivisible steps. This has a fascinating consequence. It eliminates the dreaded singularity at the center of a black hole and the beginning of the Big Bang. There is no point of infinite density because you cannot compress matter smaller than the smallest possible unit of space. Instead, the theory suggests a quantum bounce, where a collapsing universe could rebound into a new expanding one. While less ambitious than string theory in unifying all forces, loop quantum gravity deals directly with quantizing gravity and offers potential ways to test its predictions, such as subtle changes in the speed of light from distant gamma-ray bursts. Yet other ideas push the boundaries even further. Causal dynamical triangulations imagine spacetime as being built from tiny, geometric building blocks that assemble themselves. Asymptotic safety proposes that gravity might be reconciled with quantum mechanics without the need for extra dimensions or strings, if the strength of gravity changes at different energy scales in just the right way. And some physicists explore the possibility that space and time themselves are not fundamental, but emerge from a deeper, more abstract network of quantum information, much like the temperature of a gas emerges from the chaotic motion of countless molecules. Each of these approaches is a monumental intellectual effort, a different angle of attack on the same profound problem, but they all share one thing in common: a complete lack of experimental verification. We have not yet devised an experiment powerful enough to probe the Planck scale, the unimaginably tiny domain where these quantum gravitational effects are believed to become important. This is why the search for quantum gravity remains a magnificent blind spot. It is a frontier of pure thought and mathematical beauty, driven by the deep human need to find a single, coherent story for our universe. Without it, our understanding of cosmology is incomplete. We cannot say with confidence what happened at the very beginning of time, or what ultimately becomes of matter that falls into a black hole. Solving this puzzle would be more than just a Nobel Prize-winning achievement. It would represent a fundamental shift in our comprehension of reality, a new chapter in physics that could reveal wonders we haven't even begun to dream of. It would allow us to peer past the singularity and truly understand the genesis of the cosmos. And this profound challenge of merging the very large with the very small finds one of its most puzzling expressions in a paradox that threatens to undermine the very foundations of quantum theory, a paradox born in the darkest places in the universe. At the heart of every black hole lies a singularity, a point where the laws of physics as we know them cease to function. According to Einstein's general relativity, this is a place of infinite density, where gravity becomes so overwhelming that not even light can escape its grasp. But when we bring quantum mechanics into the picture, a profound and deeply troubling paradox emerges, one that pits our two greatest theories against each other in a fundamental conflict over the nature of reality itself. This is the black hole information paradox, and it begins with a seemingly simple principle from quantum physics. Information cannot be destroyed. In the quantum world, information isn't just data. It refers to the complete quantum state of every particle, its position, momentum, spin, and all other properties. The principle of unitarity states that this information is always preserved. If you could somehow track every single particle and its interactions, you should, in theory, be able to reverse time and see where everything came from. It's the ultimate cosmic receipt, ensuring that the universe's ledger is always balanced. Now, enter the black hole. Imagine a book, a complete collection of information, falling past the event horizon, the point of no return. According to classical general relativity, that book is gone forever, irretrievably lost to the singularity. The information it contained seems to have vanished from our universe. But in the 1970s, Stephen Hawking made a revolutionary discovery. He realized that due to quantum effects near the event horizon, black holes aren't completely black. They slowly emit a faint glow of radiation, now famously known as Hawking radiation. This process causes the black hole to gradually lose mass and, over astronomical timescales, completely evaporate. Here's the catastrophic problem. Hawking's original calculations showed that this radiation is purely thermal. It's random noise, like the heat radiating from a stove, and it contains no information whatsoever about what fell into the black hole. So when the black hole finally evaporates into nothingness, all that remains is this random thermal radiation. The book and all the information it contained appears to have been permanently erased from existence. This violates the foundational law of quantum mechanics. We are left with an impossible choice. Either our understanding of quantum mechanics is wrong and information can be destroyed, or our understanding of gravity and black holes is profoundly incomplete. For decades, this paradox simmered, a seemingly unsolvable puzzle. Then, in the late 1990s, a potential way out was proposed. The key might lie in a concept called holography, inspired by the work of physicists like Gerard T. Hooft and Leonard Susskind. The holographic principle suggests that all the information that falls into a black hole isn't actually lost inside it. Instead, it is encoded on the black hole's event horizon, the two-dimensional surface that surrounds it. Think of it like a cosmic thumb drive. When the book falls in, its information isn't shredded. It's scrambled and imprinted onto the surface area of the event horizon in an incredibly complex way. Then, as the black hole emits Hawking radiation, that radiation isn't random after all. It slowly and meticulously carries that encoded information back out into the universe, like a printer slowly outputting a scrambled document. By the time the black hole vanishes, all the information has been returned, preserving the quantum rulebook. This idea is breathtaking because it implies that our three-dimensional reality, including everything that happens within the volume of a black hole, might be a projection of information stored on a two-dimensional boundary. However, this elegant solution creates a new and violent problem. If information is slowly leaking out from the event horizon via radiation, it implies that the event horizon is not the peaceful place general relativity suggests. To an outside observer, the information is coming out, but to someone falling into the black hole, according to relativity, they should cross the event horizon without noticing anything special, a concept known as the no-drama hypothesis. These two pictures cannot both be true. To resolve this, some physicists proposed a truly radical idea, the firewall paradox. They suggested that the event horizon might not be a smooth gateway at all, but a seething, energetic wall of fire, a literal firewall that would instantly incinerate anything attempting to cross it. This would protect the information from being lost by preventing anything from actually falling in, but it would completely violate Einstein's principle of equivalence, which is a cornerstone of general relativity. So we trade one paradox for another. Either information is lost, which breaks quantum mechanics, or the event horizon is a deadly firewall, which breaks general relativity. The debate rages on, with new ideas constantly emerging. Some theories suggest that black holes don't evaporate completely but leave behind a tiny, information-packed remnant, though this raises questions about what such an object would be made of. Others explore the role of quantum entanglement, proposing that the particles of Hawking radiation are intricately entangled with each other and with the black hole's interior in a way that preserves information. Resolving this paradox is about far more than just understanding the fate of what falls into a black hole. It is a direct probe into the nature of reality, a test of whether quantum mechanics and gravity can ever be reconciled. The answer will force us to rewrite our textbooks, revealing whether we live in a universe that is ultimately predictable and lawful at its core, or one where the deepest truths remain hidden behind an impenetrable horizon. This struggle to understand the most extreme objects in the cosmos pushes our theories to their breaking point, demonstrating that the universe's greatest secrets are often held in the darkest places. Magnetic fields are not just a local phenomenon limited to planets and stars. They are a fundamental, though invisible, component of the cosmos on its grandest scales. We find them woven through the vast spaces between stars within a galaxy, stretched across entire galaxy clusters, and even permeating the seemingly empty voids of the cosmic web. These fields are incredibly weak, often millions of times weaker than a common refrigerator magnet, but their influence is anything but insignificant. They guide the flow of interstellar gas, shape the formation of new stars, and act as cosmic accelerators, channeling charged particles to nearly the speed of light. Yet, for all their importance, we are faced with a profound and basic question. Where did they come from? The origin of these cosmic magnetic fields is a blind spot that challenges our understanding of how the universe evolved from a smooth, featureless beginning into the complex structures we see today. There are two broad, competing ideas about how these fields were first born. One school of thought suggests they are primordial, a relic from the universe's infancy. In this scenario, magnetic fields were generated during the extreme conditions of the Big Bang or the period of inflation that followed. Tiny quantum fluctuations in the primordial plasma could have created minuscule seed fields, weaker than anything we can currently measure. As the universe expanded and evolved, these weak seeds were stretched and amplified by the motions of gas and the collapse of structures, eventually growing into the large-scale fields we detect today. If this is true, then magnetism is as fundamental to the cosmos as matter and radiation, a fossil imprint from the first moments of creation. Finding evidence for this would be a monumental discovery, giving us a direct window into physics at energies we can never hope to recreate in a laboratory. The alternative theory is that magnetic fields are a later addition, an emergent property of the chaotic astrophysics that governs galaxies. This view argues that the first fields were actually generated within galaxies themselves, perhaps by the very first stars or active black holes. One compelling mechanism involves the Biermann battery effect, a process where a swirling, heated plasma without a magnetic field can spontaneously generate one. Once even a vanishingly weak field exists, it can be dramatically amplified by the dynamo effect. Imagine the turbulent, rotating disk of a galaxy acting like a gigantic electric generator. As conductive plasma moves through an existing magnetic field, it induces electrical currents, which in turn create stronger magnetic fields. This self-reinforcing loop can take a tiny seed field and amplify it by a factor of 1 trillion or more over billions of years, effectively weaving magnetism into the fabric of the galaxy. In this case, magnetism isn't a primordial feature but a byproduct of cosmic structure, something that emerges as galaxies are born and evolve. Distinguishing between these two origins is incredibly difficult because the processes of amplification can erase the original signature. It's like trying to find the source of a river after it has flowed into a massive, turbulent ocean. Astronomers are tackling this mystery by looking for magnetic fields in the most ancient and pristine places they can find. They search for faint magnetic signatures in the extremely diffuse gas within cosmic voids, far from the messy influence of galaxies. They study the polarization of light from the most distant quasars, looking for hints that their light has been twisted by magnetic fields in the intergalactic medium during its billion-year journey to Earth. The goal is to find a magnetic field that is too large, too organized, or in too empty a region to have been created by a galactic dynamo. Finding such a field would be strong evidence for a primordial origin, suggesting that magnetism was woven into the universe's fabric from the very start. Unlocking this mystery is far more than an academic exercise. Cosmic magnetic fields play a crucial and active role in shaping the universe. They provide pressure that supports clouds of gas against gravitational collapse, slowing down the birth of new stars and determining their size and number. They influence the spectacular jets of material ejected by supermassive black holes, shaping them into narrow, powerful beams that can travel for millions of light years. And perhaps most famously, they are essential for the acceleration of cosmic rays, those high-energy particles that constantly bombard our atmosphere. Without magnetic fields to confine and whip these particles around, they could never reach the incredible energies we observe. This blind spot in our knowledge is a powerful reminder that the universe is an interconnected system. We cannot fully understand galaxy evolution, star formation, or high-energy astrophysics without first understanding the invisible magnetic forces that guide them. This hidden architecture of force fields spanning the entire cosmos is a testament to the complex and dynamic processes that have shaped everything we see, and it sets the stage for us to consider another, even more personal cosmic mystery: the nature of time itself. This profound mystery of time's direction is known as the arrow of time, and it presents us with a puzzle that is both deeply personal and fundamentally cosmic. We all feel time's relentless, one-way flow. Eggs scramble but never unscramble. Memories are made but not unmade, and we grow older, never younger. This seems so obvious, so ingrained in our experience of reality, that it's startling to learn that the fundamental laws of physics don't actually require it. If you were to take a video of most physical processes, like two billiard balls colliding, and play it in reverse, the action would still obey all the laws of physics. The equations for gravity, electromagnetism, and the nuclear forces work perfectly well backwards. They are almost entirely time-symmetric. So if the microscopic rules don't have a preferred direction, where does our overwhelming macroscopic experience of time's arrow come from? The answer, physicists believe, lies in a concept not of force, but of disorder, entropy. Entropy is a measure of the disorder or randomness in a system, and the second law of thermodynamics states that the total entropy of an isolated system always increases over time. It's why your clean room will naturally become messy if you don't put in effort to tidy it, but a messy room will never spontaneously clean itself. The increase of entropy provides a statistical arrow of time. There are simply far more ways for things to be disordered, a messy room, than ordered, a clean room. So any system left to its own devices will overwhelmingly tend toward disorder. This explains why we remember the past and not the future. The past is a state of lower entropy, and the formation of memories is a process that itself increases entropy. Our very consciousness and perception of time's flow seem to be tied to this irreversible march toward disorder, but this explanation simply pushes the mystery one step further back. If the arrow of time is defined by increasing entropy, we are forced to ask the mother of all questions: why did the universe start in such an incredibly low entropy state? The Big Bang appears to have been a moment of exquisitely specific order. All the matter and energy of the cosmos was packed into an unfathomably hot, dense, and crucially, extremely smooth and uniform state. This is a state of remarkably low entropy. A high-entropy Big Bang would have been a chaotic, lumpy mess of random fluctuations, which would have led to a very different and likely lifeless universe. Instead, we got a perfectly smooth launchpad from which entropy could then increase for billions of years, allowing for the formation of galaxies, stars, planets, and life itself. The entire history of our universe and our very existence within it is just the story of the cosmos unraveling from that initial ordered state. So why was the initial condition of the universe one of such specific, low entropy? This is perhaps the deepest version of the question why we can possibly ask. Cosmology doesn't have a definitive answer, but it offers some breathtakingly grand speculations. Some theories suggest that the low entropy of our Big Bang is not a unique event, but a single episode in a much larger multiverse. In this view, the broader cosmos is eternally inflating, constantly giving birth to new bubble universes. Most of these bubbles might be high entropy, dead voids, but statistically, a rare few will, by pure chance, pop into existence with the low entropy conditions necessary for complexity and life. We, of course, find ourselves in one of those rare, ordered bubbles. It's an application of the anthropic principle. We observe a universe with a clear past and future because we couldn't possibly exist in one without it. Other ideas dive into the realm of quantum gravity. Perhaps the initial singularity predicted by classical general relativity is replaced by a quantum bounce, as suggested by theories like loop quantum cosmology. In this scenario, our universe is not the beginning, but the rebound of a previous universe that had collapsed. That previous universe might have been heading toward a high entropy state, but the quantum bounce somehow reset the entropy clock, providing a new low entropy beginning. This would make our universe part of an endless cyclic process, with each new cycle offering a fresh start and a new arrow of time. These are compelling narratives, but they remain firmly in the domain of theoretical speculation, far from any experimental proof. The arrow of time is a blind spot that challenges us at the intersection of physics, cosmology, and philosophy. It asks why the past is different from the future, and in doing so, it forces us to confront the ultimate initial condition. The increase of entropy explains how time's arrow works, but it cannot tell us why it was loaded into the cosmic bow in the first place. Solving this mystery would do more than just complete a chapter in a physics textbook. It would illuminate the very origin of causality, change, and experience itself, revealing why our universe has a history at all. And this intimate connection between the initial conditions of the cosmos and the large-scale reality we see today leads us directly to another foundational principle of modern cosmology. This idea that the universe should be fundamentally the same in every direction and from every location is more than just a hunch. It's a formal pillar of modern cosmology known as the cosmological principle. It's the foundational assumption that allows us to do cosmology at all. Without it, we couldn't extrapolate from what we see in our tiny corner of the cosmos to make grand statements about the universe as a whole. If the universe weren't homogeneous and isotropic, then our view from Earth would be parochial and privileged, a single data point from which we could never deduce the whole. This principle is baked into Einstein's equations and is the bedrock upon which the entire standard model of cosmology, including the Big Bang theory, is built. But what if this bedrock has cracks? What if, on scales even larger than we've been able to survey, the universe reveals itself to be lopsided, lumpy, or organized in a way that shatters this core assumption? Hints that this might be the case have been emerging, creating a quiet but persistent unease among cosmologists. One of the most famous and puzzling anomalies has been nicknamed the axis of evil. This dramatic title refers to a strange alignment of patterns found in the cosmic microwave background, the oldest light in the universe. When scientists meticulously analyzed the data from the Planck satellite, they found that the fluctuations in this ancient radiation aren't entirely random. Some of the larger scale patterns appear to be aligned along a particular axis in the sky, a preferred direction that seems to point toward the constellations of Leo and Virgo. This is deeply weird. The CMB is a relic from a time when the universe was a mere infant, long before galaxies or clusters had formed. Its patterns should be the result of random quantum fluctuations, spread evenly across the cosmos with no preferred direction. The presence of an axis suggests a fundamental asymmetry imprinted on the universe at its birth, a fingerprint of a process we don't understand that may have broken the perfect symmetry we assumed was there. While some argue this could be a statistical fluke or an artifact of how we process the data, its persistence across different missions makes it an anomaly that refuses to be ignored. The potential challenges to homogeneity don't stop with light from the dawn of time. They extend to the motion of galaxies in our own cosmic neighborhood. Astronomers can map the velocities of thousands of galaxies, tracing not just how they are moving apart due to the overall expansion of the universe, but also how they are drifting together in a phenomenon known as bulk flow. These collective motions are thought to be caused by the gravitational pull of enormous overdensities of matter, vast superclusters of galaxies, and their attendant dark matter. Our current models can explain some of this motion, but observations have periodically suggested the existence of flows on such immense scales that they seem to require gravitational sources far larger and more massive than our models of structure formation should allow. One such proposed structure was the so-called Great Attractor, a gravitational anomaly in the direction of the Centaurus constellation that seemed to be pulling our local group of galaxies and thousands of others toward it. While much of this motion is now attributed to the even larger Laniakea supercluster, of which we are a part, the very fact that we are still mapping these currents highlights that the distribution of matter on the largest scales may not be as smooth and uniform as we once thought. We might be living inside a cosmic watershed whose full extent we are only beginning to appreciate. The implications of discovering a genuine breach in the cosmological principle would be seismic. It would force a radical rethink of our most basic theories. If the universe isn't the same everywhere, then the laws of physics themselves might not be constant. The strength of gravity, the mass of an electron, or the speed of light could vary in different regions of space, a concept that is currently the realm of highly speculative theory. Alternatively, it could point to something even more profound, that our universe is just one bubble in a vast multiverse. In such a scenario, the conditions of our cosmic bubble, including its apparent homogeneity, might be a local product of how our bubble formed, and the anomalies we detect could be hints of the larger, more chaotic structure beyond our horizon. This blind spot challenges our place in the cosmos not just physically but philosophically. Are we in a typical region of a uniform universe, or are we in a very special and perhaps rare pocket of consistency? The answer will determine whether we can ever truly claim to understand the universe as a whole, or if we are merely describing the properties of our own cosmic backyard. This questioning of the universe's fundamental sameness leads us to consider another class of enigmatic objects that could themselves be relics from a time before uniformity, hidden in the darkness between the stars. When we think of black holes, our minds often conjure images of stellar titans, the collapsed cores of massive stars that have gone supernova, or the supermassive behemoths lurking at the centers of galaxies. But what if there exists an entire hidden population of black holes that never came from a star? This is the compelling hypothesis of primordial black holes. Unlike their stellar and supermassive cousins, these objects wouldn't be the end result of a star's life, but rather relics from the universe's very first second of existence. The idea is that in the incredibly dense, hot soup of the early cosmos, random quantum fluctuations in density could have been so extreme that pockets of space spontaneously collapsed under their own gravity, pinching off into tiny black holes. It's a concept that turns our understanding of black hole formation on its head, suggesting that the seeds of these gravitational monsters could have been sown in the initial chaos of the Big Bang itself. The potential implications of this idea are enormous, offering elegant solutions to some of cosmology's most stubborn problems. The most tantalizing possibility is that primordial black holes could account for the universe's missing dark matter. For decades, the leading candidates for dark matter have been various hypothetical subatomic particles like WIMP or actions. But despite exhaustive searches, these particles have remained frustratingly elusive. Primordial black holes present a fascinating alternative. Perhaps dark matter isn't made of exotic particles at all, but is instead composed of countless ancient black holes scattered throughout the cosmos. their collective gravity shaping the universe while remaining completely invisible to us. This would be a stunning twist, suggesting that the solution to the dark matter puzzle has been hiding in plain sight, not in the realm of unseen particles, but in the form of ultra-compact objects we already know exist. But if they're out there, why haven't we found them? The challenge lies in their proposed nature. They wouldn't all be the same size. Theorists suggest a spectrum could exist, from microscopic black holes with the mass of an asteroid to ones several times the mass of our Sun. The smaller ones would have evaporated by now due to Hawking radiation, a process where black holes slowly lose mass, but those with masses greater than that of a large asteroid could still be around today, drifting silently through the galaxy. Finding them, however, is a detective story of cosmic proportions. We can't see them directly, so we have to look for their subtle effects. One of the most promising methods is gravitational microlensing. If a primordial black hole passes directly between us and a distant star, its gravity will act like a lens, bending the starlight and causing the star to temporarily brighten. Astronomers have run these surveys, and while they've found some intriguing candidate events, none have provided definitive proof of a widespread population of these objects. Another incredible way to search for them involves listening to the universe. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting gravitational waves from merging black holes. Some of the black holes involved in these mergers fell into a mass range that was somewhat surprising, heavier than what typical stellar collapse models predict, but lighter than supermassive black holes. This has led some scientists to speculate that LIGO might already be detecting mergers of primordial black holes. If that's true, then every time we hear that cosmic chirp of two black holes colliding, we might be listening to the echoes of the universe's birth, a direct signal from its first moments. It's a captivating possibility that connects the cutting-edge astronomy of today with the most extreme physics of the primordial past. The existence of primordial black holes would do more than just solve the dark matter problem. It would revolutionize our understanding of the early universe. Their formation requires conditions of unimaginable density and specific types of fluctuations. Finding one would be like discovering a fossil from the first instance after the Big Bang, giving us direct empirical evidence for what the cosmos was like when it was less than a second old. It could tell us about the physics of inflation, the nature of quantum fluctuations, and the fundamental energy scales that govern creation. This blind spot is a profound reminder of how the universe's deepest secrets might be hidden in the most unexpected places, not in the brilliant light of stars, but in the silent, dark ghosts of its own violent beginning. And as we search the darkness for these ancient relics, we are simultaneously confronted by a puzzle written in the oldest stars, a discrepancy in the very elements that make up our world. In the grand story of the Big Bang, there's a chapter that seems to have a glaring typo, a small but significant error written in the stars themselves. This chapter is called Big Bang Nucleosynthesis, the period within the first 20 minutes of the universe when the protons and neutrons finally cooled enough to fuse into the first atomic nuclei. It was a frantic, explosive burst of creation that forged the universe's initial supply of hydrogen, helium, and a tiny trace amount of lithium. For the most part, this theory is a spectacular success. The predicted abundances of hydrogen and helium match what we observe in the oldest regions of the cosmos with breathtaking precision, a cornerstone proof that the Big Bang really happened. But there's a problem with the lithium. According to our meticulous calculations, the universe should have created a specific, small amount of a lithium isotope called lithium-7. We should be able to find this primordial lithium preserved in the atmosphere of the most ancient stars in our galaxy, stellar relics that formed from nearly pure Big Bang material billions of years ago. But when astronomers point their spectrographs at these ancient suns, they consistently find a discrepancy. The amount of lithium-7 they detect is about 3 times lower than our models predict. It's not a small margin of error, it's a factor of 3. This is the cosmological lithium problem, a persistent and quiet anomaly that suggests something is missing from our picture of the universe's first few minutes. So where did the lithium go, or perhaps more accurately, why was it never made in the expected amounts? Scientists have explored every conceivable astrophysical solution. Maybe the lithium in these old stars is somehow sinking down from the atmosphere into the hotter interior, making it invisible to our telescopes. Detailed models of stellar physics suggest this process, known as diffusion, does happen, but likely not enough to account for the entire shortfall. Perhaps the lithium is being destroyed by some unknown nuclear process within the stars themselves after they formed. But again, the numbers never quite add up to fully solve the puzzle. The most exciting possibility is that the error isn't in our understanding of stars, but in our understanding of the Big Bang itself. The lithium problem might be a direct signal, a fossilized clue, that the physics operating in that first furious minute was different than we think. This opens the door to some truly profound ideas. Could there have been an unknown particle present in the early universe that altered the nuclear reaction rates? One candidate is a type of particle that interacts only weakly with normal matter, perhaps a supersymmetric particle or another relic from a higher energy scale. Such a particle could have affected how neutrons and protons interacted, subtly changing the pathways that led to lithium's creation and throwing off the final tally. Another, even more radical idea is that the fundamental constants of nature themselves might not be so constant. What if the strength of the fundamental forces, like the strong nuclear force that binds atomic nuclei together, was slightly different during the extreme energy of the Big Bang? A tiny variation in this force would have a dramatic impact on the delicate nuclear chains that produce lithium, potentially resolving the discrepancy. This would be a revolutionary discovery, showing that the laws of physics as we know them are not immutable, but were themselves forged in the fire of creation. Solving the lithium problem is about much more than accounting for a few missing atoms. It is a critical test of our entire understanding of Big Bang nucleosynthesis, the process that set the initial chemical composition of the entire cosmos. That initial composition determined how the first stars would form, how they would burn, and how they would eventually explode to seed the universe with the heavier elements that make up planets and life. A small error in our starting assumptions could ripple forward through billions of years of cosmic evolution. This blind spot is a powerful reminder that even our most well-tested and successful theories can harbor unresolved mysteries. It teaches us humility, showing that the universe often holds onto its secrets in the smallest of details, and that sometimes the biggest clues to the origin of everything are hiding in the faint light of the oldest stars. This meticulous forensic study of the universe's first elements inevitably leads us to a question on an infinitely grander scale, a forecast for the entire cosmic story. For all its apparent permanence, the universe is a story with a beginning, and like all stories, it must have an end. But the final chapter remains one of cosmology's greatest mysteries, a blank page whose ending will be written by the still unknown nature of dark energy. The destiny of every galaxy, star, and atom hinges on the answer to a single question. Is the force pushing the universe apart constant, or is it changing? Our current best guess, based on the cosmological constant, points toward a slow, cold, and lonely finale known as the Big Freeze or heat death. In this scenario, dark energy continues its relentless work at a steady pace. Billions of years from now, the acceleration will have pushed all other galaxies so far beyond our cosmic horizon that the night sky will go utterly black. Star formation will sputter out as galaxies are drained of their gas, and one by one, the stars themselves will burn through their fuel, dying as faint white dwarfs or neutron stars. Over incomprehensible timescales, even these stellar corpses will evaporate through a process known as proton decay, and black holes will themselves slowly dissolve via Hawking radiation. The universe will approach a state of absolute equilibrium, a uniform, frigid sea of diluted particles and radiation, where no energy can be transferred and no further event of any significance can ever occur. It is the ultimate triumph of entropy, a static, silent eternity. But what if dark energy is not a constant? What if it's a dynamic field, a force that grows stronger over time? This terrifying possibility leads to a far more dramatic and violent end, the Big Rip. In this scenario, the repulsive force of dark energy doesn't just win against gravity, it becomes infinitely powerful. First, it would tear apart the cosmic web, shredding galaxy clusters and sending individual galaxies flying into the expanding darkness. Then, as the acceleration becomes more extreme, it would attack the galaxies themselves. The gravitational glue holding a galaxy like our Milky Way together would be overwhelmed, and stars would be ripped from their orbits and flung into the void. In the final moments, the force would turn inward, planetary systems would be torn apart, and then the planets and stars themselves would be shredded. In the last fraction of a second before the end, the repulsive force would exceed the very forces that hold atoms together, and then the nuclei within those atoms. The fabric of space-time itself would be torn asunder, and the universe would cease to exist in any recognizable form. It's a catastrophic and absolute end, a definitive finale to the cosmos. There is a third, more classical possibility, though it now seems far less likely: the Big Crunch. This was the favored ending before the discovery of dark energy, when we thought the universe's expansion was gradually slowing. In this model, if there were enough matter in the universe, its collective gravity would eventually overcome the momentum of the Big Bang and begin pulling everything back together. The expansion would slow, halt, and then reverse. Galaxies would begin rushing toward each other, their light blue shifting as the universe contracts. The temperature of the cosmic microwave background would rise, eventually becoming a broiling heat that scorches the skies. The universe would collapse back toward an ultra-hot, ultra-dense state, a mirror image of the Big Bang, potentially ending in a singularity. Some theories even suggest this could be part of a cyclic universe, where a big crunch leads to a big bounce and a new expansion phase, an eternal cycle of birth, death, and rebirth. However, the discovery of accelerating expansion has made the Big Crunch the least probable of the three main scenarios, as it requires dark energy to somehow weaken and disappear, which current observations do not support. The profound challenge, the true blind spot, is that our current technology cannot yet distinguish between these fates. The difference between a constant and an evolving dark energy is subtle, a tiny change in its equation of state, a value denoted by the letter W. If W is exactly equal to -1, the cosmological constant is correct and the Big Freeze awaits. If it is less than -1, dark energy grows stronger and the Big Rip becomes our destiny. Our most powerful telescopes, like the Dark Energy Survey and the upcoming Vera C, Rubin Observatory are engaged in a monumental effort to measure this value with ever-increasing precision. They are mapping the history of the universe's expansion in exquisite detail, trying to catch dark energy in the act of changing. The answer will not just tell us how the story ends, it will reveal the fundamental nature of the energy that makes up most of the cosmos. This quest forces a humbling confrontation with the limits of our knowledge. We are temporal beings living in a mere sliver of cosmic time, trying to forecast the ultimate fate of reality across trillions of years. It is the ultimate scientific prediction, and for now, the outcome remains hidden from us, a secret held by the vacuum of space itself. And just as we grapple with the universe's ultimate destiny, we are reminded that we haven't even finished taking inventory of its present contents. Imagine you've just finished a cosmic inventory, meticulously counting up all the stars, galaxies, and nebulae you can see. You add it all together, and then you check your math against the universe's original recipe, the predictions from Big Bang nucleosynthesis. And you come up short, not by a little, but by nearly half. This isn't a case of missing dark matter or dark energy. This is about the ordinary stuff, the atoms that make up everything we see and are the protons and neutrons known collectively as baryons. According to our best models of the early universe, there should be about twice as much of this normal matter out there as we've been able to account for. So where did it all go? This is the missing baryons problem, and it's a humbling reminder that we might be overlooking gigantic components of the cosmos simply because they're incredibly difficult to see. For a long time, the leading hypothesis was that this missing matter was hiding in plain sight, in the vast spaces between galaxies, not in the form of cold, dark clouds, but as a diffuse, superheated fog known as the warm-hot intergalactic medium, or WIM. Picture the cosmic web not just as a structure of galaxies, but as a network of filaments filled with gas that has been heated to temperatures between 100,000 and 10 million degrees by the gravitational turbulence of the universe's large-scale structure. Gas this hot doesn't behave like the cold gas in a nebula. It's ionized, meaning its electrons have been stripped away from the atoms, making it virtually transparent to most forms of light. It's like trying to see the heat shimmer rising from a desert highway. You know it's there by the way it distorts the view, but you can't look at it directly. This is where astronomers had to get clever. To find this invisible, scalding plasma, they couldn't rely on traditional telescopes. Instead, they turned to the universe's natural backlights, incredibly bright, distant objects called quasars. As the light from a quasar travels billions of light years to reach us, it passes through these filaments of the WIM. The highly ionized oxygen and other elements in this hot gas absorb very specific wavelengths of that quasar's light, leaving behind a unique fingerprint, a series of tiny, telltale dips in the quasar spectrum. It's detective work on a cosmic scale, and for years the evidence was frustratingly sparse, like finding a few scattered clues but not the entire body of evidence. However, recent observations from space-based observatories like the Hubble Space Telescope and X-ray telescopes have started to successfully identify these absorption lines, providing the first solid evidence that a significant portion of the missing baryons is indeed tied up in this widespread, hot intergalactic medium. But the WIM might not be the only hiding place. Some of the missing matter could be in other elusive forms. It might be tied up in extremely low surface brightness galaxies that are too faint for our surveys to easily detect, or in the extended, faint halos of gas that surround individual galaxies but are invisible to all but the most sensitive radio telescopes. There's even a possibility that some of it exists in the form of massive black holes or other compact objects that simply don't emit much light. The challenge of tracking down every last atom underscores a fundamental truth about modern astronomy. The universe is not just made of things that shine. A tremendous amount of its structure is hidden in the dark, the dim, and the transparent, requiring us to develop ever more ingenious tools to complete our cosmic census. Solving this puzzle is absolutely critical. It's not just about accounting for lost mass, it's about validating our entire understanding of the Big Bang. The theory of Big Bang nucleosynthesis is one of the three great pillars supporting the standard model of cosmology, alongside the cosmic microwave background and the redshift of galaxies. Its prediction for the total amount of ordinary matter is incredibly precise. If we were to finally complete our inventory and the numbers still didn't add up, it would point to a serious flaw in our model. Perhaps our understanding of the nuclear processes in the first few minutes is incomplete, or maybe there's something fundamentally wrong with how we've interpreted the cosmic microwave background. Finding these missing baryons is the key to closing this chapter and confirming that we truly understand the origin of the basic building blocks of our world. This meticulous search for the universe's hidden normal matter naturally leads us to another, even more subtle mystery, one involving particles so ghostly and lightweight they barely seem to interact with anything at all. Of all the particles that make up our universe, neutrinos are perhaps the most ghostly and enigmatic. They are everywhere. Trillions of them are passing through your body every second as you hear this, coming from the sun, from cosmic rays hitting the atmosphere, and from the depths of space. They are the second most abundant particle in the universe after photons of light, and yet they are famously aloof, interacting with other matter so rarely that they are incredibly difficult to detect. For decades, the standard model of particle physics, our most successful theory of the fundamental building blocks of reality, described them as massless particles zipping through the cosmos at the speed of light. But then, experiments revealed something astonishing. Neutrinos do have mass. This wasn't just a small discovery. It was the first clear, experimental crack in the seemingly perfect foundation of the standard model. And it opened up one of the most profound puzzles in modern physics. Why are their masses so inexplicably, vanishingly small? To understand just how strange this is, we need to look at the other particles. The electron, for instance, has a mass of about 500,000 electron volts. The top quark, the heaviest known fundamental particle, has a mass over 300,000 times greater than that. But neutrinos, their masses are less than 1 electron volt. They are at least 1,000,000 times lighter than the next lightest particle, the electron. This isn't just a small difference, it's a cosmic chasm, a gaping hierarchy that demands an explanation. Why is there such a tremendous difference in scale? This question is so central that it's part of a broader puzzle known as the hierarchy problem, which asks why the force of gravity is so weak compared to the other fundamental forces. The tiny mass of the neutrino is a specific, glaring example of this same mystery playing out in the world of particle masses. The leading theory proposed to solve this puzzle is as elegant as it is mind-bending. It's called the seesaw mechanism. Imagine a literal seesaw on a playground. On one end, you have a very heavy person, and on the other, a very light child. For the seesaw to balance, the heavy person has to sit very close to the pivot point, while the light child sits far out on the other end. The seesaw mechanism applies this same principle to particles. The theory proposes that for every light neutrino we know and can detect, there exists a hypothetical, incredibly heavy partner neutrino. We've never seen these heavy partners. They would be so massive that they could only be produced in particle accelerators far more powerful than anything we can build today. In this model, the tiny mass of our familiar light neutrino is the natural consequence of the existence of its enormously heavy counterpart. The two masses are linked. As the mass of the heavy neutrino goes up, the mass of the light neutrino is pushed down. It's a beautiful and compelling idea that would neatly explain why the neutrinos we see are so light, while also hinting at a whole new world of physics at energy scales far beyond our current reach. But the mystery of neutrino mass doesn't end there. It extends its tendrils into the darkest corners of cosmology. These elusive particles were produced in colossal numbers during the Big Bang, and they still flood the universe today. Because they are so light and interact so weakly, they travel at VELOCITIES Chinese letter the speed of light for most of cosmic history. This hot motion has a crucial effect on the growth of the universe's large-scale structure. Imagine trying to build a sandcastle with dry, fine sand. It's difficult because the grains easily slip away. Neutrinos act in a similar way on cosmic scales. Their high speeds and tendency to not clump together effectively smooth out the universe, suppressing the formation of the very smallest galaxies and dark matter halos. This provides a critical link between the infinitesimally small world of particle physics and the grand architecture of the cosmos. By studying the distribution of galaxies and the cosmic web, cosmologists can actually place constraints on the sum of all neutrino masses. Our observations of the cosmic microwave background and the large-scale structure of the universe tell us that neutrino masses must be very small, perfectly consistent with what particle physicists measure in the lab. It's a stunning convergence. The biggest structures we can observe are being shaped by the properties of the smallest. This deep intertwining of particle physics and cosmology makes neutrinos a potential bridge to other great mysteries. Could they be connected to dark matter? It's unlikely that they themselves are the dark matter. They're too light and fast-moving. But some theories suggest that the same mechanism that gives neutrinos their mass, like the seesaw, might also produce a stable, heavy particle that could account for the dark matter. Or perhaps neutrinos are their own antimatter partners, a special class of particles known as Majorana particles. If this is true, it could help explain the matter-antimatter asymmetry that allowed our universe to exist. The act of a neutrino double beta decay, a rare nuclear process we are desperately trying to observe, would be the smoking gun for this Majorana nature. The quest to understand these ghostly particles is therefore not an isolated endeavor. It is a central pursuit that connects the questions of why the universe is built the way it is, how it evolved into its current form, and what unknown physics lies just beyond the edge of our current knowledge. Their tiny mass is a whisper from a higher scale of reality, a clue that our understanding of the universe is still incomplete, waiting for the next great discovery to reveal the fuller, richer picture hidden just beneath the surface. Yet for all its apparent perfection, this ancient light holds subtle, puzzling imperfections that have captivated and confounded cosmologists for decades. These are the cosmic microwave background anomalies, and they are the faintest of whispers from the dawn of time, suggesting that our universe's first chapter might have a more complex plot than we ever imagined. The most famous of these is the cold spot, a region in the constellation Eridanus that is significantly cooler than its surroundings. In a map of otherwise random fluctuations, this spot is unusually large and cold. At first, it was easy to dismiss as a mere statistical fluke, a cosmic roll of the dice that just happened to land on an unlikely number. But as our measurements have grown more precise, the cold spot has stubbornly refused to go away. It's a real feature, and explaining it requires thinking beyond our standard models. One compelling, if mind-bending, possibility is that it is an imprint of a collision with another universe in the vast multiverse. In this speculative scenario, our infant universe might have bumped into a neighboring bubble universe during the inflationary period, and the energy drained away from that region of contact left behind a cold, bruised patch on the sky. It's a radical idea, but it highlights the lengths to which scientists must go to explain such a significant deviation. But the strangeness doesn't end there. When cosmologists analyze the entire CMB map, they find evidence of hemispherical asymmetry. This means the fluctuations on one side of the sky are statistically different from those on the other. The universe's baby picture appears slightly lopsided. According to the foundational cosmological principle, the universe should be isotropic, meaning it looks the same in all directions. This asymmetry challenges that very notion, suggesting that perhaps the conditions during inflation weren't perfectly uniform across all space. It's as if the oven that baked our universe had a slight hot spot, causing one side to rise a little more than the other. Another curious feature is the apparent alignment of some of the largest scale fluctuations, which some have dramatically termed the axis of evil. These patterns seem to be curiously oriented with the plane of our own solar system, a correlation that should be utterly impossible and deeply unsettling because it hints that we might be seeing a false signal, an artifact of our own measurement, rather than a true feature of the primordial universe. So, are these anomalies just ghosts in the machine, statistical noise that we're mistakenly giving meaning to, or are they genuine cracks in the foundation of our standard cosmological model? The answer is still unknown, but their persistence drives the scientific quest forward. They could be signs of exotic physics, like topological defects in the fabric of space-time cosmic strings or textures left over from phase transitions in the early universe. Or they could be telling us that the process of inflation was more complex than the simple, single-field models we often use. Perhaps the inflattened field interacted with other fields, or inflation happened in multiple stages, leaving behind a more complicated fingerprint in the CMB. Each of these anomalies is a potential thread that, if pulled, could unravel our current understanding and weave a new, more intricate tapestry of cosmic genesis. They represent the thrilling possibility that the universe is even stranger and more wonderful than our best theories predict. A constant reminder that our map of reality is still incomplete, with blank spaces marked "Here be dragons." This meticulous forensic analysis of the universe's first light ultimately forces us to ask a more fundamental question about the stage upon which this entire cosmic drama is set. When we talk about the shape of the universe, we're not asking if it's a cube or a sphere in the way we normally imagine objects. Instead, we're talking about the very geometry of space itself, the fundamental rules that dictate how distances are measured and how parallel lines behave on the largest imaginable scales. According to Einstein's theory of general relativity, the presence of matter and energy doesn't just create a gravitational force, it actually warps the fabric of space-time, curving it. This curvature can take one of three possible forms, and the fate of the entire cosmos hinges on which one is correct. A positively curved universe would be closed like the surface of a sphere. In such a space, parallel lines would eventually converge, and if you traveled in a perfectly straight line for long enough, you would theoretically end up right back where you started. A negatively curved universe would be open, shaped like a saddle where parallel lines would diverge, spreading apart forever. Or the universe could be flat, where the rules of classic Euclidean geometry we learned in school hold true, and parallel lines remain forever parallel. For decades, this was one of the biggest questions in cosmology, and the answer came from a seemingly unlikely source: the faint, ancient glow of the cosmic microwave background. The subtle patterns of hot and cold spots in this afterglow of the Big Bang act as a cosmic ruler. By meticulously measuring the apparent size of these fluctuations, satellites like Planck have delivered a stunningly precise verdict. The data overwhelmingly suggests that our universe is flat, or so nearly flat that we cannot measure any curvature. The margin of error is incredibly small, meaning if there is any curvature, it is on a scale far larger than our observable universe. This is a profound result. A flat universe isn't just a geometric curiosity. It has a deep implication for the total content of the cosmos. For the universe to be flat, the total density of all matter and energy must be exactly at the critical density, a precise balance that prevents either positive or negative curvature. The fact that we observe this balance is a remarkable piece of cosmic fine-tuning, and it's a key pillar of our standard model of cosmology. But this answer immediately leads to a deeper and more difficult question: why is it flat? Why does the universe have this seemingly perfect, precise geometry? This is where the theory of cosmic inflation provides an elegant and powerful solution. The idea is that the universe underwent a period of exponential expansion in its first fraction of a second. Think of it like taking a tiny, crumpled piece of paper representing a highly curved, chaotic early universe and inflating it to the size of a football field. Any local wrinkles or curves become stretched out to such an enormous scale that they become imperceptible. From our perspective within that football field, our local piece of the paper would appear completely flat. Inflation doesn't just predict a flat universe, it demands it. The mechanism that drives this rapid expansion naturally flattens the geometry of space, much like how blowing up a balloon makes any small section of its surface appear flatter and flatter. However, this incredible success story comes with its own set of puzzles. Our measurements, while incredibly precise, still have a tiny margin of error. We cannot say with absolute 100% certainty that the curvature is exactly zero. It could be slightly positive or slightly negative, and that tiny deviation, if it exists, would have truly universe-altering consequences. A positively curved, closed universe would eventually stop expanding and collapse back in on itself in a big crunch. A negatively curved, open universe would expand forever, its galaxies becoming increasingly isolated in an ever-cooling void. The fact that we measure it to be so perfectly flat suggests an almost unbelievable fine-tuning of the initial conditions. This is the flatness problem, one of the key issues that inflation was designed to solve. Yet the possibility of a slight curvature remains a tantalizing blind spot, a reminder that our measurements, while extraordinary, are still limited to the universe we can observe. This question of geometry is far more than an abstract mathematical exercise. It is intimately connected to the ultimate fate of everything and forces us to confront the very initial conditions of reality. If the universe is truly and exactly flat, it tells us that inflation almost certainly happened, and it tells us that the total density of the cosmos is perfectly balanced. But if future, even more precise measurements were to ever detect a slight curvature, it would send shockwaves through the world of cosmology. It could mean that our understanding of inflation is incomplete, or that there is something fundamentally wrong with our models of dark energy and dark matter. The geometry of the universe is a foundational property, a silent architect that has been shaping the destiny of galaxies since the first moment of time. As we use the rules of general relativity to map this vast cosmic terrain, we are inevitably drawn to a frontier where those very rules break down, where the smooth geometry of spacetime itself must give way to the fuzzy, probabilistic world of the quantum. We've journeyed through the vastness of cosmic voids and the explosive mystery of fast radio bursts, but now we confront a puzzle that lies at the very heart of reality itself: the baffling transition from the fuzzy, probabilistic quantum world to the definite, classical universe we see around us. This isn't just a question for tiny particles in a lab. It's a profound cosmological blind spot because the entire universe, in its infancy, was a single quantum system. So how did it make the jump from a realm of mere potential to the concrete reality of galaxies and stars? This is the measurement problem, scaled up to the grandest possible level, and it forces us to ask, how does our objective reality actually emerge? In the quantum world, particles don't have definite properties until they are measured. They exist in a superposition, a blend of all possible states, like a coin spinning in mid-air, being both heads and tails at once. This strange behavior is perfectly described by the wave function, a mathematical entity that contains all the probabilities for what we might observe. The problem, famously illustrated by Schrödinger's cat, is that this indefinite state seems to persist until an observation is made, which then collapses the wave function into a single, definite outcome. This works well enough for an experiment in a box, but in cosmology, we run into a logical paradox. If the entire universe was once a quantum object, who was there to observe it and collapse its wave function? There was no outside observer. The universe is everything, so how did it ever choose a single state to be in? One compelling solution comes from a process called decoherence. This isn't a magical collapse, but a more gradual process of the quantum world interacting with itself. Imagine that spinning quantum coin. Left perfectly isolated, it remains in its superposition. But the moment it interacts with its environment, a single air molecule bumps into it, or a photon of light grazes its surface. That interaction effectively leaks information about the coin's state into the wider world. The delicate quantum coherence is destroyed, and the coin appears to settle into a single classical state, either heads or tails. In the context of the early universe, the incredibly hot, dense plasma would have been a frenzy of such interactions. Particles were constantly bumping into each other, and these relentless interactions would have caused the universe's wave function to decohere at an astonishing rate, making the quantum probabilities quickly solidify into the classical facts we now observe. It's a powerful idea that explains our definite reality without needing a conscious observer, framing the classical world as an emergent property of quantum systems interacting with their environment. Yet, decoherence, while explaining how quantum superpositions become effectively classical, doesn't fully solve the deeper philosophical problem of why only one outcome is realized. This is where interpretations of quantum mechanics venture into truly mind-bending territory. The many worlds interpretation offers a radical answer. The wave function never actually collapses. Instead, every possible quantum outcome does happen, but each one plays out in its own separate, non-communicating branch of reality. In this view, at every quantum decision point, the entire universe splits. There's a universe where the cat is alive and another where it is dead. There's a universe where a particular galaxy formed slightly differently and another where it didn't form at all. Our subjective experience of a single, definite reality is just a perspective. We only witness one thread of an infinitely branching multiverse. For cosmology, this is a breathtaking proposition. It suggests that the initial quantum state of the universe didn't choose one path but gave rise to all possible paths, and we simply inhabit one of countless parallel cosmic histories. Other interpretations seek to modify quantum mechanics itself to resolve the issue. Objective collapse theories propose that the wave function collapse is a real physical process, triggered not by observation but by something else like gravity. Perhaps when a quantum system becomes too large or massive, the gravitational influence of its own particles causes its superposition to spontaneously collapse. This would mean there's a fundamental threshold where quantum behavior gives way to classical behavior, and the early universe would have crossed that threshold extremely quickly as it expanded and cooled. Another approach, known as quantum Bayesianism or cubism, sidesteps the problem entirely by arguing that the wave function doesn't represent an objective reality, but rather an individual agent's subjective beliefs and probabilities about the world. In this view, the quantum classical transition is not a physical process but an update in our information reality, is not emerging from probability. Our knowledge of it is. This blind spot is more than a technical debate. It strikes at the core of what we mean by reality. It asks whether the universe we see is the only one, or just one page in an infinite book of possibilities. It challenges us to explain how the definite structure of the cosmos, the specific arrangement of galaxies, the precise values of fundamental constants could have been selected from a sea of quantum potential. The answers we gravitate toward reveal our deepest intuitions about the nature of existence. Do we live in a single, objective universe that somehow made a choice? Or are we part of a vast, branching multiverse where every possibility is realized? Or is reality, at its most fundamental level, somehow dependent on interaction or even information itself? This unresolved puzzle forms a crucial bridge between the quantum mechanics of the very small and the classical cosmology of the very large, and it forces us to stare into the abyss between probability and fact. As we grapple with the emergence of our reality from a quantum beginning, we are inevitably drawn to the ultimate question of that beginning itself, to the moment where all our current theories of physics break down completely. At the very heart of our cosmic story, according to our best theory of gravity, lies a profound and deeply unsettling concept, the initial singularity. General relativity, when we rewind the tape of the expanding universe all the way back, predicts that everything we see, every galaxy, every star, every atom, was once compressed into an infinitely dense, infinitely hot, and infinitely small point. This is the moment of the Big Bang, a mathematical point where the curvature of spacetime becomes infinite and the known laws of physics simply cease to function. It's the ultimate dead end for our equations, a place where our understanding of reality hits a solid wall. An infinity in physics is not a number, it's a sign. It's a glaring red flag that our theory is incomplete, that we've pushed it far beyond its limits and into a domain where it can no longer reliably guide us. This singularity represents the greatest blind spot of all, for it blocks our view of the very beginning, leaving us to wonder if we can ever truly speak of a beginning at all. The most promising path forward, the tool we believe we need to break through this wall, is a theory of quantum gravity. General relativity is a classical theory. It describes the smooth, warped fabric of spacetime beautifully, but it doesn't account for the fuzzy, probabilistic nature of the quantum world that dominates at the smallest scales. To understand the universe when it was smaller than a single atom, we need a theory that can marry these two descriptions. We need a framework where gravity itself is quantized. Several candidates offer breathtakingly different visions of what could have replaced the singularity. Loop quantum cosmology, for instance, suggests there is a smallest possible unit of space, a tiny quantum of volume. In this view, you cannot compress the universe into an infinitely dense point because you run into this fundamental graininess of spacetime. Instead of a Big Bang singularity, the theory proposes a big bounce. Our expanding universe could be the rebound of a previous cosmos that had contracted, part of an endless, cyclical process of birth, death, and rebirth. There was no absolute beginning, just an eternal transition from one state to another. String theory, another leading contender, also seeks to eliminate the singularity by replacing the point-like particles of the standard model with tiny, vibrating strings. In this framework, the extreme energies of the early universe might be described without infinities, painting a picture of a violent but finite genesis. Other ideas, like the no-boundary proposal from James Hartle and Stephen Hawking, use a complex mathematical approach to suggest that time itself behaved like a dimension of space in the very earliest moments. In this model, the universe would have no initial boundary in time, much like the Earth has no edge at the North Pole. You can travel north indefinitely, but the concept of north loses its meaning at the pole itself. Similarly, asking what happened before the Big Bang might be as meaningless as asking what is north of the North Pole. The beginning is smoothed out into a finite, self-contained geometry. These scientific models inevitably brush up against profound philosophical questions that have captivated humanity for millennia. Did the universe have an absolute beginning, a first moment of time? Theistic interpretations often see this as compatible with a concept of creation, while others seek a purely physical explanation. Or is the universe eternal without beginning or end? The cyclic and bouncing universe models offer a compelling vision of an everlasting cosmos, where every ending is merely a prelude to a new beginning. This leads to the staggering possibility of the multiverse. Perhaps our Big Bang wasn't the beginning, but simply a beginning, our local bubble of space-time inflating from a larger, eternal meta-universe that is constantly giving birth to new universes, each with its own random physical laws and constants. In this view, the question of an ultimate beginning might be forever beyond our reach, as we are trapped within our own cosmic bubble, unable to see the greater whole. This blind spot is so fundamental that it lies at the very limits of science itself. It forces us to confront what is even knowable. Can we ever develop a theory that explains its own initial conditions? Or are we forever destined to trace the cosmic history back to a veil, beyond which we can only speculate? The search for answers is driving the most advanced experiments we can conceive, from particle colliders that recreate the high-energy conditions of the early universe to telescopes that peer back to the first light after the Big Bang. Each new piece of data helps us test these wild and wonderful ideas. Resolving the mystery of the initial singularity wouldn't just complete a chapter in a textbook. It would represent a fundamental leap in human comprehension, revealing not just how our universe began, but the very nature of time, existence, and reality itself. This quest to understand the origin of everything, from the infinite to the infinitesimal, naturally leads us to another puzzle that asks why the fundamental forces of nature are so vastly different in strength. Of all the forces that shape our universe, gravity holds a unique and paradoxical position. It sculpts galaxies, governs the orbits of planets, and dictates the large-scale structure of the cosmos. Yet, on the human scale, it is laughably feeble. A simple refrigerator magnet can defy the gravitational pull of the entire Earth, effortlessly lifting a paperclip against a force that holds the Moon in orbit. This staggering imbalance isn't a trivial observation. It is one of the most profound and embarrassing problems in all of physics, known as the hierarchy problem. To grasp the sheer scale of this weakness, consider the numbers. The electromagnetic force is 1,000 trillion times stronger than gravity. That's a 1 followed by 36 zeros. The strong nuclear force, which holds atomic nuclei together, is 100 times stronger still. This isn't just a small discrepancy. It's a cosmic chasm that screams one undeniable truth. Our current understanding is missing a fundamental piece of the puzzle. Why does this matter so much? Because this incredible weakness of gravity is woven into the very fabric of our reality, influencing everything from the stability of atoms to the ultimate fate of the universe. If gravity were significantly stronger, stars would burn through their fuel at a ferocious rate, collapsing into black holes long before life could possibly evolve on any orbiting planets. The universe would be a violent, short-lived place. If it were even slightly weaker, matter would never have been able to clump together to form the first stars and galaxies. The cosmos would be a forever expanding, thin and lifeless mist. The fact that we exist to ponder this question suggests that the strength of gravity, like so many other fundamental constants, is exquisitely fine-tuned. But fine-tuning is not an explanation, it's a mystery begging for one. Physicists abhor such incredible coincidences, believing there must be a deeper, more natural reason for this vast hierarchy between forces. One of the most captivating explanations transports us into the realm of extra dimensions. In our everyday experience, we live in 3 spatial dimensions and 1 of time. But what if there are more? String theory, a leading candidate for a theory of everything, requires the existence of at least 6 extra spatial dimensions, curled up into a space so infinitesimally small that we cannot perceive them. This idea offers a stunningly elegant solution to the hierarchy problem. Imagine gravity is not weak at all. Instead, its strength is simply diluted because it is the only fundamental force that can leak out into these extra dimensions. Picture it like this: the other forces, electromagnetism, the strong and weak nuclear forces, are like waves confined to the 2-dimensional surface of a pond. They are intense and powerful on that surface. Gravity, however, is like a sound wave emanating from the pond. It spreads out into the 3-dimensional air above it, becoming vastly diluted and weaker from the perspective of someone floating on the surface. In this scenario, gravity only appears weak to us 3-dimensional beings because we are not sensing its full strength, which is spread out through a higher dimensional space. This mind-bending concept leads to a thrilling possibility. If these extra dimensions exist, we might one day be able to detect them, not by seeing them directly, but by creating them. In powerful particle colliders like the Large Hadron Collider, scientists are smashing particles together at velocities Chinese letter the speed of light. If extra dimensions are real, these colossal energies could be enough to create microscopic black holes or see evidence of particles called Kaluza-Klein modes, which would be the telltale sign of gravity accessing these hidden realms. Finding such evidence would revolutionize our understanding of reality, proving that the cosmos is far vaster and more complex than our 3-dimensional perceptions allow. It would show that the hierarchy problem isn't a flaw in our universe's design, but a clue to its true higher dimensional architecture. Of course, extra dimensions are not the only game in town. Other theories propose that the weakness of gravity is related to the properties of the hypothetical particle that carries it, the graviton. Perhaps the graviton has an unusually small mass, or maybe it interacts with matter in a uniquely suppressed way. Some models even suggest that what we perceive as gravity in our universe is actually a secondary, emergent force, much like how the force of pressure in a gas emerges from the collective collisions of countless molecules, rather than being a fundamental force itself. Each of these ideas is a bold attempt to solve a problem that sits at the uneasy intersection of particle physics and cosmology. The strength of gravity determined how quickly the universe could cool after the Big Bang, how readily primordial density fluctuations could grow into galaxies, and how dark energy would eventually come to dominate the expansion. It is a number that has written the entire history of the cosmos. Solving the hierarchy problem would therefore be more than a theoretical triumph. It would be a key that unlocks a new chapter in physics. It would reveal why our universe has the specific properties that allow for complexity and life. It might even show us that the fundamental constants we hold as fixed and immutable are not so constant after all, but could be the local, accidental outcome of a much larger and more varied cosmic landscape. This realization that our physical laws might not be universal sets the stage for an even more expansive and speculative idea, one that suggests our entire universe is just one tiny bubble in an infinite, frothing multiverse. This staggering weakness of gravity, this incredible fine-tuning of the constants that allow for our existence, leads us to a breathtakingly grand and controversial idea. What if our universe isn't the only one? The multiverse hypothesis is perhaps the most expansive and speculative concept in all of cosmology, a proposition that our entire observable cosmos, with its specific laws and constants, is just one bubble in a vast, frothing cosmic foam of universes, each with its own unique and random physical rules. This isn't science fiction. It's a serious, though highly debated, theoretical consequence of our two most powerful ideas about the early universe: eternal inflation and string theory. The concept emerges as a potential solution to one of the most perplexing questions in science. Why does our universe seem so perfectly, almost miraculously, fine-tuned for life? The strength of gravity, the mass of an electron, the value of the cosmological constant. If any of these were even slightly different, atoms would never form, stars would never ignite, and life as we know it would be impossible. The odds of getting a universe that works by sheer random chance seem astronomically low. The multiverse offers a dramatic way out of this conundrum. If there are an infinite number of universes, each with randomly selected physical parameters, then it's no surprise that we find ourselves in one of the rare, life-permitting ones. We are the inevitable outcome of a cosmic lottery with nearly infinite tickets. The most scientifically grounded path to the multiverse comes from the theory of eternal inflation. This model suggests that the inflationary period that jump-started our universe isn't a one-time event that began and ended. Instead, it's a perpetual, self-reproducing process. Picture the inflating space-time as an endlessly rising loaf of raisin bread, but where each raisin itself inflates into a new loaf, and each raisin in that new loaf does the same, ad infinitum. In this ever-expanding meta-universe, the process of inflation never stops overall, but within it, in countless localized regions, inflation does end. In each of these regions, the energy of the inflattened field decays, reheating that pocket of space into a hot, dense soup of particles, a big bang. Each of these regions becomes a separate, causally disconnected, bubble universe, forever isolated from the others by the ever-inflating space between them. In this vast ensemble, the fundamental constants and even the number of spatial dimensions could be set randomly as each bubble forms, creating a breathtaking diversity of cosmic realms, most of which would be sterile, lifeless voids, but a rare few, by pure statistics, would have the golden ticket. String theory, the ambitious attempt to unify all forces and particles, adds another layer to this multiverse vision. The theory suggests there may be a colossal number of possible stable configurations for the extra dimensions it requires, perhaps 10 to the 500 or more. Each configuration would correspond to a different vacuum state, a different set of physical laws and constants. This landscape of possible universes is not just a theoretical abstraction. If eternal inflation is true, then this entire landscape could be physically realized, with each bubble universe manifesting a different point in the string theory landscape. Our universe, with its specific particle properties and force strengths, would then be just one data point in a near-infinite ensemble of possibilities. This combination of eternal inflation and the string landscape forms the most robust scientific framework for the multiverse, transforming a philosophical curiosity into a plausible, though still speculative, physical theory. However, this grand vision comes with a monumental catch: testability. The defining feature of these other universes is that they are permanently beyond our observational horizon. The space between our bubble and any other is expanding faster than light can traverse it, making them utterly inaccessible to any signal, measurement, or probe. This leads many critics to argue that the multiverse hypothesis is not science, but metaphysics, an untestable, unfalsifiable concept that lies outside the bounds of empirical inquiry. If we can never observe another universe or detect any evidence of its existence, can it truly be considered a scientific theory? Proponents counter that we might find indirect evidence. For instance, if our universe collided with another bubble in the distant past, it could have left an imprint on the cosmic microwave background, like a bruise on the sky. Some have even pointed to the infamous cold spot as a potential candidate, though this remains highly speculative. Others suggest that the multiverse might make statistical predictions about the values of constants we should expect to measure in our own universe, given that we exist to observe them, an application of the anthropic principle. This push against the boundaries of science forces a deep philosophical reckoning. If the multiverse is true, it would represent a Copernican revolution on the grandest possible scale, demoting our universe from a unique creation to a single specimen in an infinite cosmic zoo. It would provide a naturalistic explanation for fine-tuning, removing the need for a designer, but in doing so, it might also undermine the very nature of scientific explanation. If everything that can happen does happen in some universe, then our laws of physics are not universal, immutable truths. They are merely local bylaws, the arbitrary rules of our particular cosmic neighborhood. This doesn't destroy science, but it reframes its goal, from discovering the unique, fundamental laws of reality to mapping the distribution of laws across the multiverse and explaining why we observe the particular slice that we do. It's a shift from certainty to probability, from determinism to a vast cosmic statistics. This blind spot, therefore, is more than just a puzzle about the cosmos. It's a challenge to our understanding of knowledge itself, pushing us to ask what science can and should hope to explain about the ultimate nature of reality. And as we contemplate the possibility that the very laws of physics might be variable across a hidden multiverse, it forces us to ask a more immediate and testable question. Could those fundamental constants be changing even here within our own universe as time unfolds? We take for granted that the rules of the universe are fixed and unchanging. The speed of light in a vacuum is always 299,792,458 meters per second. The strength of the gravitational force between two objects is always determined by the same universal constant. These numbers are the bedrock of physics, the immutable parameters we plug into our equations to describe everything from the spin of an electron to the expansion of the cosmos. But what if this bedrock is shifting beneath our feet? A small but persistent group of physicists and cosmologists are investigating a truly radical possibility: that the fundamental constants of nature are not constant at all, but have slowly changed over the billions of years of cosmic history. This isn't a minor adjustment. It would be a revolution that forces us to rewrite the textbooks and rethink our entire understanding of physical law. The prime suspect in this investigation is a number known as the fine structure constant, often denoted by the Greek letter alpha. This constant might sound obscure, but it is one of the most important numbers in all of physics. It is a pure, dimensionless number that governs the strength of the electromagnetic force, which is responsible for holding atoms together, making chemistry possible, and creating the light we see. Its value, approximately 1/137th, determines how tightly electrons bind to an atomic nucleus. If alpha were much larger, atoms would be smaller and stars would burn their fuel too quickly for life to emerge. If it were much smaller, atoms might not even form. Its precise value seems exquisitely fine-tuned for a complex universe, which is why it's a key focus for those asking if constants might drift. How do you possibly measure a change in a fundamental constant across billions of years? Astronomers use the universe itself as a time machine. They point powerful telescopes at the most distant quasars, which are extremely bright galactic cores billions of light-years away. The light from these quasars has traveled through clouds of interstellar gas on its long journey to Earth. These clouds absorb specific wavelengths of light, leaving behind a unique barcode of dark lines in the quasar's spectrum, an absorption spectrum that tells us what atoms were present in those clouds and how they were behaving. Crucially, the precise positions of these absorption lines depend intimately on the value of the fine structure constant. If alpha had a different value when that light was absorbed eons ago, the spacing between these lines would be slightly different than what we measure in laboratories on Earth today. Some teams, using this incredibly precise forensic technique, have reported tantalizing evidence that alpha might indeed have been very slightly smaller in the distant past. The claimed variation is minuscule, a few parts in a million over billions of years. But if true, the implications are explosive. Other teams, using different telescopes and methods, have found no such variation, leaving the scientific community in a state of cautious suspense. The measurements are at the very bleeding edge of our technological capabilities, susceptible to incredibly subtle systematic errors that are fiendishly difficult to rule out. Is the signal real, or is it a ghost in the data? The question remains one of the most hotly debated and intriguing blind spots in modern cosmology. Should these findings ever be confirmed, the ramifications would be staggering. The entire edifice of modern physics is built on the assumption that these constants are, well, constant. General relativity, the standard model of particle physics, and our models of stellar evolution all rely on this foundational idea. If the strength of electromagnetism has changed over time, it means the laws of physics themselves have a history. They have evolved. This would force a profound revision of our theories, likely pointing toward a deeper, more dynamic framework that unites the forces in a way we haven't yet imagined. It could mean that the universe shortly after the Big Bang operated under a slightly different set of rules than it does today, which would completely change our understanding of how the first elements formed and how the earliest structures began to clump together. The constancy of physical law is a pillar of science, and discovering it to be a variable would shake that pillar to its core, opening a new chapter in our quest to understand why the universe is the way it is. This profound question about the very fabric of reality inevitably leads our curiosity to the most intimate and mysterious frontier of all, the nature of our own consciousness and its place in the cosmos. After exploring the potential variability of the very laws that govern reality, our journey brings us to the most intimate and profound mystery of all, the nature of our own consciousness and its perplexing relationship with the cosmos. This is a frontier where established science begins to blur into deep philosophy, a realm of speculation that pushes the very boundaries of what we can ask, let alone answer. It's not a traditional blind spot in observational cosmology, like a missing galaxy or an undetected particle. It is a conceptual chasm, a question about the observer's role in the grand scheme of existence. Some of the most daring and controversial theories in physics venture into this territory, suggesting that consciousness might not be a mere passive byproduct of the universe, but could be fundamentally intertwined with its very fabric. This idea often finds a foothold in the bizarre world of quantum mechanics, particularly in the infamous measurement problem. In the quantum realm, a particle exists in a blur of probabilities, a superposition, until it is observed or measured, at which point its wave function collapses into a single, definite state. This raises a deeply puzzling question. What exactly constitutes a measurement? The mathematics of quantum theory doesn't specify. The Copenhagen interpretation, one of the earliest and most well-known views, practically requires an observer, a conscious entity, to complete the process and bring about a concrete reality. This has led some thinkers to propose that consciousness itself is the crucial ingredient that collapses the wave function, that the universe only takes a definite form when it is perceived by a mind. It's a notion that places sentient beings at the very center of cosmic creation, a modern echo of philosophical idealism. Another perspective emerges from the many worlds interpretation, which offers a very different but equally mind-bending view. In this model, the wave function never collapses. Instead, every possible quantum outcome actually occurs, but each one plays out in its own separate, branching universe. In this vast multiverse, your consciousness isn't causing a collapse. It is simply following one specific thread of an infinite tapestry of possibilities. Your subjective experience of a single, definite reality is just that, your unique path through the endlessly forking tree of quantum events. Here, consciousness is more like a reader following one storyline in a choose-your-own-adventure book where every choice is simultaneously made. These ideas, while intellectually thrilling, remain firmly in the realm of speculation and are viewed with deep skepticism by the majority of mainstream physicists. The primary criticism is that they attempt to solve a problem in physics by invoking something consciousness that we understand even less. Explaining one mystery with another, deeper mystery is not considered a valid scientific solution. Furthermore, the field of decoherence has provided a powerful physical mechanism that explains how quantum superpositions rapidly become classical through interaction with their environment, seemingly removing the need for a conscious observer altogether. From this viewpoint, consciousness is an emergent property of complex neural computation, a fascinating phenomenon that arose through evolution to help organisms navigate the world, but not a force that dictates the behavior of fundamental particles. Yet, the persistence of these questions highlights a crucial point. Our exploration of the cosmos inevitably circles back to us. Cosmology isn't just about mapping distant galaxies or cataloging particles. It is a quest to understand our place in the grand scheme of things. The fact that we can formulate these questions, that we can peer back to the first moments of time and grapple with the nature of reality, is itself a remarkable outcome of cosmic evolution. We are the universe become self-aware, a way for the cosmos to look back upon itself and ask, "What am I?" This philosophical dimension is inescapable. Whether consciousness is a passive passenger or an active participant, our drive to comprehend the darkness beyond our current understanding is what propels science forward. It reminds us that the journey to map the external universe is also fundamentally a journey to understand the internal universe of the mind that is doing the looking. This ultimate convergence of the objective and the subjective represents the final frontier of our curiosity, the point where hard data meets profound wonder, setting the stage for our final reflection on what all these mysteries, if solved, would truly mean for our story of everything. And so we've traveled together from the invisible grip of dark matter, holding galaxies together, to the repulsive push of dark energy, tearing the cosmos apart. We've stood at the edge of a black hole's paradox and peered back to the very first second of time, confronting mysteries that defy our current laws of physics. Each of these blind spots, the Hubble tension's conflicting numbers, the profound matter-antimatter imbalance that allowed us to exist, the elusive nature of time's arrow, isn't just a gap in a textbook. They are more like cosmic invitations, calls to adventure that promise to shatter our current understanding and usher in a new era of discovery. They remind us that science, at its heart, is not a dusty collection of facts but a dynamic, living process of inquiry. It's a story that is constantly being rewritten, a map of reality that is forever being redrawn as we push further into the unknown. This journey is a powerful lesson in humility. For all our brilliance and technological achievement, we have to accept that roughly 95% of the universe is made of stuff we cannot see and do not understand. The fundamental laws we hold as sacred might be mere local bylaws, or they could be changing over billions of years. The cosmos, in its infinite complexity, consistently reveals that our knowledge is provisional, always subject to revision with the next great observation or the next revolutionary idea. This isn't a sign of failure, it's the very engine of science. It's what makes the quest so profoundly exciting. The universe is under no obligation to conform to our expectations, and that is what makes every new discovery so thrilling. The most beautiful part is that this story is still being written, and you are a part of it. Every time you look up at a starry night with a sense of wonder, every time you share a fascinating article or a video about a new space telescope discovery, you are participating in this grand human endeavor to understand our place in the cosmos. The answers to these questions won't just be found by a lone scientist in a lab. They will emerge from a global community of curious minds, all contributing to a shared pool of knowledge. Your curiosity is the most important ingredient in that process, so as we conclude this cosmic tour, I want to thank you for your time and your curiosity. If this journey through the universe's greatest mysteries sparked your imagination, consider liking this video and subscribing to the channel. It truly helps us continue exploring these incredible topics and share them with more people. The conversation doesn't end here. I'd love to hear which of these blind spots you find the most fascinating, or if you have your own theories. Let's keep the discussion going in the comments below. Never stop looking up and never, ever stop questioning. The next great revelation is waiting just beyond the edge of our current